Good morning, everyone. Welcome back to the ESA RemTech 2021 webinar series. Thank you for joining us this morning. I'd like to acknowledge our sponsor for today's session, Abacus Enterprise. So thank you to the gang over at Abacus. Also, before we get started, I'd like to, ESA respectfully acknowledges that we are located on Treaty 6 territory, a traditional gathering place for diverse Indigenous peoples, including the Cree, the Blackfoot, the Métis, the Nakota Sioux, the Iroquois, the Dene, Ojibwa, and Saulteaux, Inuit, and many others whose histories, languages, and cultures continue to influence our vibrant communities and work. So for today, we have 4 presentations, and we'll take a 15-minute break approximately, depending on our timing, and then we have another four presentations. Some other housekeeping presentations will be available. I'll send out an email either today or tomorrow with a link to the video along with a link to the presentations. So we have one more webinar next week. EnviroTech 2022 is coming up in April in Calgary at the Hyatt. Details will be sent out shortly with the call for abstracts. RemTech East, our new event, happening every second year, is in Niagara Falls at the Falls View Casino. Call for abstracts is already up and early bird registration is up. And then RemTech, of course, returns every fall back in Banff. So to get started, our first speaker of the day is replacing Megan James is Paul Nicholson with Geosyntech Consultants. I'll just get Paul's presentation up here for everybody. And Paul speaking on Have You Got Methane? Latest trends in vapor mitigation for brownfields.
Perfect, Joe. You're seeing the right screen? Just because it popped up again to share my screen again.
Good question.
Yeah, should be.
Let me just.
I can see it, Paul.
You can see it, yeah, the full. Okay, because it's presented for you on one screen. I got 2 monitors, just make sure.
Yeah, so, you're all good.
Great.
Looks good. Sounds good. Thanks, Paul.
Perfect. Thanks. Morning, everyone. My name is Paul Nicholson. I'm a senior engineer with Geosyntech Consultants located out of Guelph, Ontario. And today we're talking about methane and the latest trends in vapor mitigation for brownfield sites. And as Joe mentioned, Megan James contributed to this presentation, but she's off today, so I'll be presenting on her behalf. So first off, why we care about methane. We'll talk through what methane is and how it can be an issue. We'll talk about some key considerations related to vapor intrusion investigation methods for methane. I'll sort of do a broad discussion about risk perspectives of vapor intrusion in Canada. And then I'll go through a couple examples of methane vapor intrusion mitigation. So as many of you probably know, methane is explosive, between 5% and 17%. It's also an asphyxiation hazard. And also the biodegradation of methane forms carbon dioxide, which can also be an asphyxiant. And so one of the key differences between methane versus other subsurface contaminants like chlorinated solvents is that we can get advective flow or pressures through the generation of methane in the subsurface. And also when it comes to sort of methane remediation and mitigation, it can sort of change and vary depending on the regulations, depending if it's sort of anthropogenic sources or natural sources. So obviously landfills are a major source of methane across Canada. This plot here sort of shows 160 different landfills across the Greater Toronto area, many of which are located near residential and commercial properties, and especially as the city expands, we get closer or building on top of some of these former waste sites. So Montreal also has a number of former waste dump sites throughout the city. And obviously, as sort of, again, same issue as sort of Toronto, as land prices increase, we start building towards or on top of these areas. So it's not just landfills that can create methane as an issue. Obviously, landfill gas is a large proportion of it related to brownfield sites. We could also get mine gas or mains natural gas issues as well, but also the sort of the natural methane sources such as wetlands and peatlands. And you're able to sort of this table sort of shows the composition of sort of these different methane sources, and being able to sort of look at the ratios between methane and CO2 or hydrogen sulfide or other sort of carbon dating methods to try to figure out if your source of methane is from a landfill or from maybe a natural source. But definitely something to sort of consider as you're building on sites. In Alberta, we also sort of have old non-production wells. Most of these wells are not located sort of around sort of high density urban areas, more rural. But as again, properties expand, these wells can still release methane and can still be an issue. So for methane sort of in Canada, in some cases, methane is being handled through the municipalities. For example, the city of Burnaby has incorporated methane gas into their local building code. This is due to naturally occurring methane that can be found within the sort of boundaries of the city of Burnaby. And so methane is often sort of covered from sort of more of a municipality perspective. One of the leaders in this would be the city of LA and the county of LA down in Southern California. So they have developed sort of development of buffer zones around naturally surfacing coal tar and crude oil. So they have a lot of methane issues as a result of this. So in this sort of Southern California area, there's about 6 different cities and 2 counties that have specific guidance related to methane. And they're sort of one of the first areas. And so a lot of these jurisdictional information around LA sort of gets adopted by other municipalities as they're developing their own methane protocols. So the city of LA, their documents show that you have to investigate a site if it's within 300 meters of a landfill or 100 meters of an oil well. Also, the mitigation requirements are based on sort of your conceptual site model, and specifically so your measured concentration of methane, and also the pressure of the methane gas in the subsurface, which is unique to methane, as I discussed about sort of generating pressure gradients related to methane. And then based on that, you can sort of determine various sort of mitigation methods. So that's kind of the, why we care about methane, especially related to brownfield redevelopment sites. So next, what I want to discuss is sort of how vapor intrusion investigation methods may get tweaked a little bit if you're looking at a methane site. So from a general vapor intrusion perspective, hopefully most people are sort of familiar with evaluating vapor intrusion at sites. We go through a multiple lines of evidence approach. And here we're trying to develop sort of a conceptual site model of the vapor intrusion pathway. And this multiple lines of evidence, as shown on the right-hand side, involves a number of different factors that can impact vapor intrusion, and their importance will depend on sort of where in the profile you're looking. But we are not just looking at sort of multiple chemistry data points. It's not just the measurement of deep soil gas, shallow soil gas, indoor air. We actually want to really look at building effects, the permeability of the subsurface, depth to water, and then geological features as part of this multiple lines of evidence approach. So when it comes to methane and petroleum hydrocarbons, the vertical profile evaluation is important. Here we're really looking to identify where aerobic biodegradation is occurring in the subsurface and what that impact is on our overlying building. So the plot here on the right-hand side, ground surfaces is the top of that box where the sort of the black arrow is, and we're going deeper through the subsurface, and then concentrations of VOCs, O2, and CO2 are increasing from left to right. So down at your water table, especially if you have a petroleum hydrocarbon source floating on the water table, you'd have high concentrations of petroleum hydrocarbons, high concentrations of methane. Up at the ground surface, we're going to have atmospheric concentrations of oxygen, and then oxygen is obviously going to sort of diffuse into the subsurface. And at some depth, you're going to find an optimal location where your oxygen concentration is feeding your bacteria, and they're degrading petroleum hydrocarbons and methane in place quite rapidly. And you get this sort of rapid decline, as you can sort of see in the plot here. So what we're looking for is to identify where this aerobic biodegradation zone exists. Is there enough oxygen in the subsurface to promote this? And we can see orders of magnitude degradation over generally just a few feet in the subsurface. And as part of this, we're also trying to look at advective flow and understand pressure gradients. So just to kind of compare this to the typical chlorinated vapor intrusion site versus hydrocarbons and methane. On the left-hand side, we have your typical chlorinated site with dissolved phase plume going under a building, and you get quite a large vapor plume in the vadose zone, where these contaminants like PC and TC are not degrading in the vadose zone. Versus on the right-hand side, where we have a hydrocarbon or methane site, where we got oxygen transport into the subsurface, and we're degrading those contaminants before they can migrate up. So we end up with sort of a smaller plume and a smaller footprint. So those are kind of the, the differences when we're investigating methane in petroleum hydrocarbon sites. Just a short topic on sort of safety. Obviously, we're in an existing building. If it's there, we're looking at sort of subsurface concentrations of methane. We have worked on sites where we're drilling into environments where there's sort of 90% methane beneath the slab, where you could actually, you're already above the upper explosive limit of 17%, but you could actually have your methane dilute through the explosive range and cause issues. So considering the health and safety side of things when drilling in these high methane environments is really important. And the other bit I just want to mention is that we do a lot of in situ bioremediation here at Geosyntec, and we have at sites, especially when we're doing remediation under buildings, where you can generate methane, especially at a shallow water table. So just be considering the actual generation of methane at your sites. And if you're going to be drilling at a site where maybe formerly there wasn't methane, but now they have produced methane, it's important. Also from the field screening side, as part of the collection of representative samples for vapor intrusion, if we're filling SUMA canisters, for example, we're going to use helium as a leak check compound, just to make sure we don't have any leaks through the sample train. However, methane has a positive interference on the helium meters. And so if you have methane in your sample and you screen that with a helium meter, you're going to see a helium response where you think you may have a leak, but it's not actually helium in your sample, it's methane in your sample. So being cognizant of this and understanding that, so that you're not wasting time trying to fix leaks that aren't actually there. Vice versa, some methane meters, if you're trying to screen at a methane site, also have interference with helium. So it goes sort of both ways, where helium can actually interfere with your methane meter as well. So it's important to sort of just understand that and take that into consideration when you're sampling. So next, I just want to look at sort of the risk perspective of vapor intrusion across Canada. There's a few federal vapor intrusion guidance documents like the CCME guidance and the Health Canada vapor intrusion guidance. And then provincially, vapor intrusion is sort of mentioned throughout most of the provincial and territorial guidance documents that we have. The three sort of main ones are the Atlantic province document that was written, I think, originally in 2016 and updated in 2019. We have the Ontario draft guidance for vapor intrusion. Then in British Columbia, we have the contaminated sites regulation, and then part of that is sort of Protocol 22, and then the recently written contaminated sites approval professionals vapor intrusion document. So these are sort of the main sources, and what I'm going to do is just sort of maybe discuss this sort of the differences between Ontario and British Columbia with sort of the predominant sort of documents that that we use. So as part of that comparison, I just want to discuss the concept of attenuation factors. So an attenuation factor we use in evaluating vapor intrusion, and it is the ratio of indoor air concentrations to some subsurface concentration. And the reason we use attenuation factors is measuring the concentration of vapors in indoor air can be difficult. Now with methane, there's not usually a lot of interior sources of methane that may cause issues, but if you're looking at things like benzene, PCE, you can have background factors that will influence the indoor air concentration. So it's much easier to measure a subsurface concentration than use an attenuation factor to predict what the indoor air concentration may be. And so the difference between Ontario and BC is how we sort of use these different attenuation factors. So starting off with British Columbia and Protocol 22. So in this, in British Columbia, they use a subslab attenuation factor, sort of highlighted here, of 0.02. So what that's saying is that there's a 50-fold dilution from the sample you collect in the subsurface to predicting what the indoor air concentration would be. However, what BC do, which is different than other provincial jurisdictions, is they have vertical attenuation factor changes. So your attenuation factor will increase as you move down with depth, which is unique to British Columbia. And so this is part of your conceptual site model, and investigating a site is to determine what depth your concentrations are at and what attenuation factor to use. Now in Ontario, we have sort of two empirical attenuation factors. The same 0.02 factor for residential properties, but slightly different is for commercial and industrial land, we use an attenuation factor of 0.004. So that's a 250-fold dilution from subsurface to indoor air. And that really takes into the account that commercial buildings have thicker slabs, larger building volumes, and generally higher air exchange rates. But then the question becomes, what about biodegradation in these attenuation factors? And each province handles biodegradation slightly differently as well. So starting off with Ontario allow you to use an attenuation factor, an additional attenuation factor of 10 or 100 times to account for biodegradation. And it generally depends on the depth of what your contamination is at. So for example, if you have low concentrations below 1 milligram per liter and your concentrations are at a depth of 1 meter, you can use a 10-fold attenuation factor. If it's as deep as 3 meters, you can apply a 100-fold dilution attenuation factor. And again, this changes if your concentrations are slightly higher, then you need more depth down to 2 or 4 meters. And then again, if you're sort of near NAPL concentrations above 50 milligrams, they're looking for 3 meters to 5 meters for that 10 to 100 times attenuation factor. So then looking at British Columbia, again, BC Protocol 22 uses a slightly different criteria. So they use something called an attenuation adjustment divisor, which is the same as sort of an attenuation factor, just slightly different name. So they have, for biodegradation, their biodegradation factor is just a straight 10-fold at your site. There's no changes based on depth or concentration. But they do have an additional factor of 50 times if you have a parkade. So this is a parkade attenuation adjustment divisor. So it's a 50-fold change if you have a first level parking garage. And then they also have a lateral attenuation factor. So this is your offset between where your property that you're looking at versus your source, anywhere from sort of up close up to about 30-meter offset, you can use an additional attenuation factors. So there's sort of a specific difference between BC and Ontario. So next, looking at methane mitigation systems. And so the typical vapor intrusion mitigation system design is looking for a subslab depressurization system. So most guidance through ASTM and the EPA is looking to depressurize the subslab environment of a building by 6 to 9 pascals. So what we do is we generate a vacuum under the slab of a building. Any vapors that come up under that building sort of get captured and vented above the roof line. However, this standard approach to vapor intrusion mitigation isn't necessarily optimal for the design of methane mitigation systems. So with methane, we want to enhance biodegradation. So we want to bring oxygen into the subsurface and degrade that methane in place such that we don't have to then pull it through a subslab depressurization system. So we want a higher flow rate, so we want more oxygen into the subsurface. Generally, when you have a higher flow into the subsurface, you need higher permeability. And when you have a higher permeability subsurface, you can't apply as much of a vacuum to the subsurface. I'll sort of show this through an example of two sort of generic systems. So this is depressurization versus venting. So on the left-hand side, we have a typical residential house, and we have a fan where we're extracting from air beneath the subslab. We're generating a vacuum under the slab of that building. What this causes is generally advective flow down through the floor slab. So in these types of systems, you're also actually extracting conditioned indoor air from within your building. So your heating and your cooling air, a proportion of that is getting pulled through the floor and vented out of your roof. In sort of a venting type system, which we like to use for methane, was we have an air inlet pipe. So as the fan extracts from sort of one side of the building, we're pulling atmospheric air down to the subsurface. This creates a high oxygen environment under the slab where you can then enhance biodegradation in the subsurface before you extract those vapors from your building. But the question kind of comes down to is what sort of vacuum do you then generate under that scenario? And are you meeting sort of that 6 to 9 pascal requirement? So I just want to give you some examples of mitigation systems we've installed recently related to methane. The first example is a site in the GTA. The property of interest is sort of the red outline box there. There was about 5 or 6 existing residential properties at the site, and then they were going to get redeveloped into a higher density residential property. And we are next to a former landfill. So the future development looked like this. It's actually a full first level parking garage, and then built over top sort of multi-story residential properties. That's the first phase there. The second phase is sort of in the gray closer to the landfill, is more high-rise residential buildings. So the mitigation system we're looking at is sort of the more rectangular shape for the first side of the development. So this is rotated slightly. The landfill is sort of towards the bottom of the page. This is the lower parking garage and sort of the design of our vapor extraction system. And so down in this corner, we did some investigation prior to the construction of the building. Actually, the developer evaluated the existing properties to measure methane in the subsurface and indoor air. And there was no methane in indoor air, obviously, which is great. That's great data to have in terms of how vapor intrusion is going to occur at future buildings you put in. But there was methane detected along the edge closest to the landfill. That sort of makes sense with our conceptual site model of where that methane may be coming from. And so as part of the system, we have a number of perforated extraction pipes under a vapor barrier across the footprint of the building. And so they're extracting vapors out through fans. But because we had methane in sort of one bottom corner of that building, we designed these pink, shown on this drawing, pink air inlet pipes. So these are air inlets at the front of the building that are open to atmosphere, so that when we extract vapors from under the building, it draws atmospheric air into the subsurface environment. What that does is it generates like a bioactive zone where we've got high oxygen concentrations near where those methane concentrations were detected, such that any methane that's there, we can degrade in place before we extract it. This is beneficial because then we can use non-explosion proof fans. We don't have to worry about methane entering our piping network and moving through fans that may not be explosion proof if we get high enough methane concentrations, but only targeting it to the air of the building that really needed sort of methane abatement. The next site, this is a 100,000 square foot, I guess, warehouse facility. This had documented methane on the site in some areas with some decent pressures, and this was some naturally occurring methane at this site. So what we used is we created an aerated floor system using a product called Cupolex. In the bottom left photo, these are the black domes. You can see in the background it's starting to pour the concrete floor over top of the domes. In the top right, you can see what it looks like underneath. These domes are arched and they create a completely open void space under the concrete slab. And so rather than having perforated pipes run through a gravel layer, you have a completely open conduit under the slab of your building, which enables the mitigation of a system with very small fans. You can propagate vacuum equally and much more easily across the entire void space. And so we extracted sort of at the rear of the building, and at the front of the building, we installed air inlet pipes again to bring oxygen into that subsurface void space and create a venting flow across the building that introduced oxygen. In this case, we were able to install at this property without a vapor barrier, and also we were able to convert the system to a completely passive system due to that sort of enhanced biodegradation. We didn't measure any methane in the subsurface of this after it was constructed. So finally, on a recent project, it was a property with a former underground storage tank that was going to get an excavation down to a few meters below ground surface. So as they were going to dig sort of a hole underneath the footprint of the building, we took advantage of that hole and installed air inlet pipes deeper into the subsurface rather than directly beneath the slab. So in this case, we have vapors moving up. There was concern that even following excavation due to some fractured rock at the site, there would be hydrocarbon and methane concentrations in the rock that may come up following the excavation and construction of the building. So by installing air inlet pipes deeper within the subsurface, we can bring oxygen right down to sort of those depths where the vapors are. What this allows is the generation of that aerobic biodegradation zone, so the deeper under the slab of the building. That way then when we install our extraction system, we're extracting concentrations that have been reduced or non-existent. And we can use non-explosion proof fans, and it also can help us on the air permitting side, which I'll discuss next. So most jurisdictions in Canada do not exempt vapor mitigation systems from some of the air permitting requirements. So in Ontario, this is covered by the ECA or EASR process. So you do have to apply to the ministry for these mitigation systems if you are discharging contaminants to the atmosphere. And you also have to consider sort of noise issues as well. Metro Vancouver, for example, have their own approvals branch for vapor mitigation systems. But some of the benefits of enhancing biodegradation in the subsurface is, as I mentioned, you could use non-explosion proof fans, which are much cheaper and much more cost effective, or even convert your system to a passive system if you're not discharging methane or petroleum hydrocarbons. And also, you may potentially be exempt from a permit if you're not actually discharging contaminants into the environment because you're degrading them in place. So just some sort of take-home messages at the end here. Methane is a concern, not just sort of from landfills, but from many different sources. Traditional mitigation system criteria may not be the most correct approach for mitigating methane sites in particular, because of that need to sort of introduce oxygen into the subsurface, because we want to use that biodegradation to our advantage when we're designing these systems. And that we can tailor a mitigation system to the site conditions based on that conceptual site model understanding to sort of save installation costs and then long-term operational costs as well. And with that, I will leave it there.
Thank you, Paul. Great presentation. Valuable information there to be aware of when working on site. If anyone has any questions, please type them in the question box of the chat and I'll relay them to Paul before we move on to our next presentation. Paul, what's your email address just for people that want to contact you?
Yeah, it's not actually up there. So it's pnicholson@geosyntech.com.
Okay, so pnicholson@geosyntech.com if people want to reach out directly to Paul and ask him questions. Paul, I don't see any questions as of yet. So with that, again, thank you. And we'll move on to our next presentation.
Perfect. Thanks.
Our next presenter is Bruce Tunnicliffe with Vertex Environmental. See, Bruce has his presentation up, which is great. Bruce will be speaking on remediating bedrock. What was once impossible is now possible. 3 case studies. Bruce, over to you.
All right, thanks, Joe. Just want to check, you can hear me okay?
Yeah, we got your presentation and you sound great. Thank you.
Okay, and I can't see myself, but is my webcam on?
It's off.
It's off? Would you like it on?
I don't see it myself, so.
Oh, here it is.
There it is, it's coming.
All right, just wanted to make sure I got these details sorted out here. But,
yeah, all it is a black box right now. Do you have a slider on your camera?
oh, interesting, hold on. Yeah, let me see what webcam it's using here. Sorry, Joe, I'll just take a sec here and we'll, oh, it's using my other one. Okay, I see.
Perfect. There you go.
All right, I have 2 webcams, so I might minimize myself here so I'm not staring at me. Okay, so thanks, Joe, and thanks, Isa, for setting this up. I think it's webinar series is really good to do during COVID, especially. So I'll get going. The title of my talk here is remediating bedrock. What once was impossible is now possible, and I'll go through 3 case studies here. And Joe, sorry to ask, can you see my mouse if I move it around?
Yes, we can. Yep.
Yes, you can. Okay. So the outline of the talk today is I will go over bedrock, why it's so difficult to remediate, why it has been so difficult. Before jumping right into 3 case studies, they're all bedrock related. The first one has petroleum hydrocarbons, including LNAPL. The second one is a heavy metal hexchrome plume. And the last one is chlorinated solvents with PCE. I'll then conclude with takeaways, lessons learned, and any questions. And so just so you know who I am and why I'm speaking, I just thought I would share a picture of me. This is about 25 years ago. I did my master's degree at Waterloo, where I was interested in fractured rock, and I did an experiment on oxidation of using permanganate in a fractured rock network. I did a lab experiment, and so I'm pretty happy to be able to continue with bedrock along my career here. I founded Vertex in 2003, and I just want to clarify that Vertex is a contractor. I know there's another Vertex in the industry, which is a consultant, but we work with consultants and work coast to coast. So some of the things that we do here on this slide. So to hop into it, the difficulty with bedrock remediation. In 2013, the US Department of Defense wrote that one of the most challenging environmental restoration issues is determining how to deal with contaminants that have seeped into fractures in bedrock and are a continuing source of groundwater contamination. And so I'll touch on that continuing source. And the US Geological Survey at the same time also noted that remedial action is delayed or stymied by the complexity of contaminated fracture rock aquifers. And so this was just a few years ago that this was written, and I think a lot has developed in the last 8 years. And I'll go over some of these case studies of what we've done in that time. So why is bedrock remediation so challenging? It's challenging because the fracture network can be very complex, and thus the contaminant distribution can also be very complex as well. The secondary porosity, which you don't think of rock as having a porous nature, but it does. The contamination can soak into the rock, and it's very difficult to get out. So it travels along the fracture network, and then it soaks up into the rock. Bedrock's also pretty expensive, so it's very hard to access. It's expensive, so it's very easy for a contaminant to enter a pretty large fracture. But then when you're trying to figure out where it goes, the cost to drill a well in rock is much more expensive than in a shallow soil. And bedrock's also challenging because the plume length can be long. If you imagine a very thin fracture, some fractures are as thick as the width of your hair, and they can transmit plumes very far. That volume is very small compared to porous media. And then the groundwater flow velocity can be quite fast through an open fracture, and this complicates remedial efforts. And so just to show this visually, porous media, I think it's generally accepted that you can call it 30% porosity, but what's the porosity of bedrock? It's really variable. It can be 1% up to 10%, but much smaller in general than porous media. And so if you spill 1,000 liters into both, it's going to go much further in a fractured rock network. And one of the largest problems with bedrock remediation is shown by this illustration here. If you've got separate phase NAPL, so like a non-aqueous phase liquid that enters a fracture network here in early time, in intermediate time, it diffuses into the secondary porosity of the rock matrix, and later all your NAPL's gone, but it's present within the difficult to access secondary porosity. And this is the classic definition of back diffusion. It's a real problem. So you can remediate your fracture network, but then your plume back diffuses out into that same fracture network, causing a long-term problem. So with those thoughts in mind, we'll jump right into the case studies. Case study 1 is a petroleum hydrocarbon related cleanup. It's a confidential site. It's located in Ontario. It's a former retail fuel outlet, so there's underground tanks, dispenser island, automotive service operations occurred. And so the ground was contaminated with petroleum hydrocarbons, including light non-aqueous phase liquid, separate phase, dissolved phase. And in situ chemical oxidation was completed by others in 2015, 16, and 17. And then Vertex came on site later from 2019 to 2021, so this year. And I'll show you data up to this year with this case study. This is an aerial view of the site. The site is the focus area of the site is outlined in the red box here. residential area to the left. To the south here, it might be hard to see, but there's quite a large apartment building that is down below, and the rest of the area is open and vacant. This is the monitoring well network. Most of the wells are located in the vacant area where the automotive area was, but of course the plume migrated towards and under the adjacent apartment building. In terms of what the subsurface looks like, the depth to bedrock was anywhere between 1 and 3 meters, but the depth to groundwater was about 3 or 3.5 meters. So it's a full bedrock aquifer. Above is tighter material, silty material, and then underlain by shale bedrock. So shale can be somewhat friable. You're able to dig into it a little bit. And so it's a shale bedrock aquifer. So in terms of the plume and the extent of the separate phase El Napo, it's kind of outlined here. It's hard to see, so I'll just color it in for you. It almost looks like a funny fish or something. But the plume is in blue, and the separate phase El Napo is shown in orange. So this is just to give you an idea of the size of the plume. In terms of concentration, the F1 dominated the plume, and it was up to about 10,000 micrograms per liter in the non-Napo areas. And this is compared to a standard of 750, so many times the standard. And even though the F2 concentrations, more diesel range was less, it's still 10 times the standard in the area. So this is the plume. And the El Napo was sheen to about 30 centimeters in thickness in that area. So we'll take a look at analytical as I walk through this case study. And the analytical that we'll look at is in these yellow circles here. So just to give you an idea of the distribution of the data, it's distributed across, we've kind of randomly picked these points. There's about 22 monitoring wells that were contaminated, and we'll just select these to show you the trends. So of the 6, here is the historical data. This is a plot of BTEX and petroleum hydrocarbon concentration on the left and time on the bottom. And you can see these wells just fluctuate over time between 500 up to 10,000. If it was more than 10,000, I just stopped it at 10,000 just to have the plot a little easier to see. And then these are the 3 ISCO injections that were completed. And so in terms of what occurred after 2 injections, you can see that there was some promise. Some of the results came back quite low after a couple injections. But as is the problem with bedrock remediation, the back diffusion occurred, and you can see that in general, the concentrations after the second oxidant injection were kind of similar to the beginning. This is why bedrock is difficult. And then after the third injection, not much changed. So I think the client was, looking for something different here. It's proven that bedrock remediation is tough. So what occurred is after the chemical oxidation, El Napo persisted, significant petroleum hydrocarbon concentrations remained, and the consultant, I think, did a pretty good job of stating why. They said that the increases are interpreted to be a result of the just oxidative conditions, but causing mobilization to groundwater of contaminants from within the soil bedrock matrix. So I think they're totally right there. I think back diffusion was the problem, and the Napo got in, it's just having a hard time getting out. And so a new consultant was brought on the property, and Vertex joined that consultant in 2019 to take a look at what we could do. And what we did is we said, well, if you have El Napo and you've had a history of it continuing to come back even after trying to remove it, just don't fight it, see if we can dig it out. So just straight, brutal approach. And for back diffusion, you can't dig out a bedrock aquifer. It's way too costly. But for the rest of the plume, the problem was back diffusion. So why fight it? We'll go with this trap and treat approach, which was relatively new to the industry, is an activated carbon-based approach. And I'll just show you that in terms of how new, the US EPA came out with this fact sheet on activated carbon-based technology and talked about the various types of amendments and the approaches, and that was just in April 2018. So just before Vertex got involved with the work. In terms of what it is, just so you know, up in the top left, this is a picture of an activated carbon molecule, or well, actually not even molecule, just a particle. Lots of open space that contaminants can migrate in and get stuck. But as with some pump and treat systems, if you have the activated carbon and you're pumping, then you have breakthrough and then your carbon is spent. And so the thing that is done for in situ remediation is you create biological processes which occur on the near surface of the activated carbon particle. And through electron transfer and other processes, as the petroleum hydrocarbons accumulate and reside within the activated carbon, it becomes a great site for these bacteria to continue to eat the petroleum. And so you get this great thing occurring in the ground where you've got both adsorption, if you can see this new slide here, occurring, and then degradation. And in the middle then is this remedy. So you trap it and you treat it and you have a regenerating carbon. And so we had never tried it before in a bedrock environment like this, but we thought that it would work. And this is what we proposed, and the client said, let's go for it. And so we weren't without knowledge. We had done some trap and treat work before this, and this is just a logarithmic scale to show you that this was a historical chlorinated solvent site, actually, where we applied those BOSS 100. And after we applied it, the adsorption and the treating worked. And being a logarithmic scale, this came from 500 down to 10. And so we're pretty confident that we could apply it at this site. So here is a picture of the site. If you can see this coming up on your picture, it's relatively flat and open. You can see some of the stick-up casings and also the apartment building there in the background. So we started digging out the source area. You can see in the upper part there, it's relatively easy for the excavator to move through. As we got deeper and the bedrock became more competent, or different areas of the site, we just needed different attachments to really try and break up the rock, even jackhammer-like, in order to remove. And we saw an apple in the fracture network. We're really glad that we dug it out. This is just a picture of the side as we were starting to backfill. You can just see the various layers of the shale bedrock, and we were pretty successful in digging out the area where we had to, where the separate phase it existed. So just another picture. I hope these are coming through okay for everyone on the webinar here. This is the size of the area that we ended up excavating, and you can see again that apartment building in the back. But it was near impossible to try to dig out this entire plume. So then the second step was moving to an in situ remediation for the rest of the plume. And how that was done is we cored through the rock. We had to case the upper part of it and then core through into the rock to leave an open borehole that then we could inject into. In terms of how many boreholes did we put in, we had done some pilot testing, which I don't have enough time to go over that in this presentation, but did pilot scale testing, and we ended up finding appropriate spacing, and we put in 142 of these injection boreholes outside of the Napple area. When we backfilled the excavation, we also added in this BOSS 200 product in order to continue to treat anything that was left in the plume. And so how did we undertake the injection? We had a packer system, and it was a double packer system. And so just zooming in to look at it, we could inflate the top and the bottom, leaving about a 1 foot interval. And we injected over numerous discrete intervals in every single of those 142 boreholes. It took months to do, but we distributed, based on our calculations, 146,000 liters of a mixed BOSS 200 material into the ground. So it's quite the undertaking. We'll just go back to the analytical again. So these are the 6 wells that I was showing you before with the oxidation work. And here is the, again, the results of the oxidation work with concentration on the left and time on the bottom. And so I'll just move that back. Some additional sampling was completed, and this was the start of our injection. And all the wells were sampled after we were completed, and we were extremely pleased to see as we had hoped, all 22 wells, well, actually except for one, decreased below the standard. The entire site was clean. There was one location that up in this left corner that still had a minor exceedance, but we were very pleased with the result. The El Napo was removed by excavation before. None of the 22 wells were clean afterwards. 21 of 22 met the standard. And we don't have the data yet for the next sampling round, but based on what we've done at other sites, we believe it'll stay low. And so ISCO, really some of the thoughts is ISCO should only be applied to bedrock after careful consideration. It has difficulty with separate phase NAPL. It also has great difficulty with back diffusion and the secondary porosity. The excavation was great, removed the NAPL, and so if you can dig. And this trap and treat material, it absorbs the plume, it treats it, and it, I think, directly addresses bedrock back diffusion. It does that by the rate of biodegradation is greater than the rate of back diffusion, and therefore it suppresses the plume over a long period of time. And so we're pretty happy. 21 and 22 monitoring wells clean, the other one marginally over, and we'll probably just do a spot injection around there and take care of that. So that was a petroleum hydrocarbon case study. The other ones are a bit quicker to go through, and so we'll hop on to the second one. This is bedrock and heavy metals, a hex chrome. This is also a confidential site. This was a hexavalent chrome plating facility. There was underground tanks that were there that were filled with this hex chrome liquid. Of course, the tanks leaked. They didn't leak. I guess I wouldn't be speaking about it here. There's also historical spills. The neighbor did a phase 1 ESA contemplating selling their property, and they found pretty high concentrations of hexavalent and trivalent chrome right on the property boundary between this plating facility. And so we did bench and pilot scale testing was completed. Full scale is being designed right now. And so what I will go over is the bench and pilot scale results. And who knows, maybe we'll present the full scale at a later time. So this is where the site is located. If you can see the red lines here around this longer property. Unfortunately for this client, groundwater flows a bit to the right, and there's an entire residential subdivision, which always gets the regulators upset. This is a zoom in of this property, and this is the neighbor just up that did the phase 2. Just so you can see what this area looks like and kind of the size of it. This is a consultant's drawing of it showing the monitoring well network and where the wells were put in. Fortunately, the wells that were put in down in the cul-de-sacs down here came back non-detect, so the plume is somewhere between these wells and the property boundary. This is just a rough sketch of the outline of the interpretation of the plume. And it's pretty incredible. The hex chrome concentrations in the source area is 2.3 million parts per billion, which is very high. The hex chrome standard is 140, and so we'd need a 99.99% reduction if we were going to successfully treat the source area to the standard. So pretty tall order to do. Down gradient here, you see this one well is 77,000 micrograms per liter, and so to reach the hex chrome standard, we need a 99.8% reduction, and in bedrock. So is this even possible to do? This is just a cross section, or not a cross section, a borehole of the site, and so the weathered shale is again is the bedrock type. Above it, tight material. This is a picture of, we decided to do the bench scale testing, and the consultant sampled water from the source wells, and this is just a picture of what it looked like when we brought it into our lab in order to start our treatability testing. Super concentrated hex chrome, just pure yellow. It's pretty wild to see. And I had to throw in this picture. This isn't the site, but this was another hex chrome site we worked on. and it was very contaminated as well. And this is just during a dig or that it rained, and this is the color of the rain when it contacted the soil at the site. So you can tell when you're in a contaminated area of hexchrome, you know what it looks like there. Hexchrome is different than trying to destroy petroleum hydrocarbon. The reason it's an element of the earth, so you can't just destroy it like you can a molecule of benzene. And so I don't need to go on this in detail, but basically what the process would be here is we take a dissolved component, we have electron donors, and we create a solid byproduct. So we're looking at complexation and precipitation and then absorption onto the bedrock as our method of addressing the dissolved phase contaminant in the ground. So just back to this again, we had a question is, before we actually did the bench, is in situ heavy metal treatment by 99.8% even possible? And we had done some other work, and so we took a look at that, and there was some zero valent iron column studies that we had done where we set up various media in order to try and treat some other heavy metals. And the results of that are just shown here quickly. We had as high as 40,000 micrograms per liter of zinc, and at a site, actually it was even higher than that. That's the water that we got. And when we ran it through our columns, we were able to get a 99.98% reduction of that, in addition to other metals as well. So we were comfortable that we could probably roll through with that. So when we did the testing for this site, we took a look at various electron donors shown here. Our method was we had 1 liter containers, we put in silica sand, and then the remedial amendment, we added the water, placed in the dark, let sit 1 week, sampled the water, what would happen. And so here are the results. This is a logarithmic chromium plot here on the left. The baseline, which was just water by itself, was here. The control, the sand was very similar. You don't add anything, you don't have any change. We had some issues with the molasses when it gummed up pretty bad, and there was lots of biological activity, so it came back at 5. But these ones, ferroblack, ZVI, and Boss 100 all came back at half. This is half the detection limits. Came back at less than 0.5. We just put in a 0.25. So yeah, we think that if you add the right amendment, you can complex and get pretty substantial reductions. The source water, we just experimented with zero valent iron, and we were able to see incredible 99.998% reduction. So the theory works. So we could apply this to the site. Will it work when we did pilot scale testing? So we did a variety of pilot scale plots. This is the site plan. We had a ferroblack pilot on the back side of the building. We installed various injection wells around an existing monitoring well in order to inject. We did a zero valent iron injection in the source and a zero valent iron injection in the plume area in order to determine what would occur. And I'll just show you quickly the layout here. We injected around MW11. MW11 was located also by MW10514, which we actually didn't expect to see much influence on. And I'll just show you the plot here. These are the concentrations. I'll just move it over and up to show you what we are dealing with at the time that we did the pilot. And after we injected zero valent iron into the injection portholes, we got a pretty good reduction. MW11 was right in the middle, and you can see that it decreased to about 91%, and we even saw great influence at the adjacent well. So that gave us good confidence. I'll zip through this quick because I see I'm getting close here on my time. The concentration here of the plume was a little bit less. You can see the concentration was around 15,000, so not as high, but still incredibly high. And after we injected in that pilot scale area, the adjacent monitoring wells, which we didn't inject into, we just inject around, showed really amazing results. So MW1 was in the middle, MW10314 was just off to the side. We were able to achieve a 99.4% reduction in the bedrock aquifer when we did the pilot. And even at the adjacent well, which wasn't even really in the area that we were injected, we saw a 96% decrease. So just to wrap up this case study, and the second one is super quick. Groundwater treatment, I think, is possible in the field. At bench, we saw great reductions. At pilot, we also saw the reductions that we probably needed. And so we're going to go with zero valent iron as a feasible solution to complex the hexchrome and drop it out of the aquifer. And full scale is about to be implemented. So we'll see how that goes in the next year, but we're looking forward to that. Final case study that'll be really quick is with chlorinated solvent. This property is a confidential site. It used a dry cleaning solvent, PCE. A developer purchased the site and they wanted to transition to a residential redevelopment. And it had to be fully remediated, no risk assessment, because they didn't want people buying on a risk-based property. The PCE concentrations were actually pretty low, only about 40 micrograms per liter versus 17 microgram per liter standard, so just annoyingly above the guideline. And for remediation, we decided to run with an extraction system in order to try to pull the plume in to see if the concentrations got higher or lower, depending, because if there was an unknown source, you'd probably find it. And then we did a shallow injection of BOS 100 and a deeper injection of inactivated carbon. Here's a picture of the site, a site plan. The bedrock was a bit deeper at about 7 meters below ground. There was a shallow plume in the lower area, and the deeper bedrock plume was shown generally by this green circle. And so the red are some of the deeper bedrock injection points that we had put in, and there was in addition a bunch more shallow injection points, which are not shown on the drawing. So the results for the groundwater extraction system, we pulled one out and started drawing on the aquifer. And here are the results. You can see immediately the concentrations all went below the 17, but as the difficulty with bedrock is, there's a secondary porosity and it bounced right back. And so we need to do more than just groundwater extraction to solve the problem. And so we had a couple of injection events, and afterwards we've seen sustained low chlorinated solvent concentrations at the site, well below the standard of 17. And we're pretty pleased with this bedrock remediation result as well. So to wrap this one up, I think groundwater extraction really helped to understand the plume. Like there was no hot spots. If there was something really contaminated nearby, I think we would have picked it up. The concentrations would have increased. And again, activated carbon-based product controls back diffusion and then allows natural bio to occur. And the result for this one is a clean site. So just in closing, I'll just say that performing bedrock remediation, I think some takeaways, lessons learned is just address LNAPL by aggressive means if you can. Like we did excavation in case study number 1, and the site came back with great results. The back diffusion is a major problem, so use a remedial amendment that can handle back diffusion. So we used trap and treat or zero valent iron, long-term products that'll last for a long time in the ground and continue to address back diffusion. And that we found that in situ injections can work if you have the proper drilling technique. You know, you do the pilot, you understand the site, you can make it work. So even though in 2013 there was lots of negativity there about bedrock remediation, I just wanted to say that once considered impossible, I think is now possible with regards to bedrock remediation. Thanks. I'll take any questions.
Thanks, Bruce. Got one question. I'll make it 2 questions for you. To start with case study 1, with the PHC, how long did you expect the AC to continue to bind PHC before it was spent?
So that's a good question. So we've used this approach, the BOS 200, at a number of properties. And so even though we don't have long-term data at this site, the other sites that we've used it at, it's been a few years that that it's happened. The product is new, and so how many years? Is it going to be 20 years that it does it? I'm not 100% sure. But as long as you have enough electron donor in the ground, and so because it's a biological process, At some of the sites, we've had to add a bit more sulfate in order to allow the bacteria to continue with anaerobic biodegradation, which is the key method that's used for this. And so I would expect the activated carbon to be a long-term material that's in the ground, and as long as the biological activity continues, that it'll regenerate itself for many, many years.
And then at the time of breakthrough, would you expect the biological degradation would have degraded all of the petroleum hydrocarbon, or would treatment need to be applied again?
Oh, I see. So I think that question, so I think the assumption behind that question is that it's like a pump and treat system where once your carbon is spent, you need to replace it. So that's not the case for this, because in a pump and treat system, normally you've got a high flow rate, high masses coming in. The rate of your material coming in biologically, it's faster than what the bugs can treat. When you've got a, diffuse activated carbon injection that you've put all over your entire aquifer, it actually regenerates itself. And lots of bench studies have shown that this is the case. And so I don't believe you would have to reapply the activated carbon. Similar to the answer to my first question, you would have to apply the materials, the nutrients that the bacteria may need to continue to survive. So I think the activated carbon you do not have to add again, but you might have to add food for the bacteria. Hopefully that answers the question.
Okay, and then one quick one before we move on. For the second case study, the chromium is not removed from the aquifer, but it's simply less bioavailable and therefore presents less risk to the receptors. Is this correct?
Yes, that's correct. And so, and one issue that we're looking at, and I'll say it right out here, is how much mass of hex chrome will come out and will it clog the fracture network? We believe the fractures are large enough that that won't occur. But it is a question that we're looking at. So unlike a petroleum hydrocarbon where you destroy your molecule, you don't destroy it, chrome, because it's element of the earth, you complex it. And so you do leave a bit of residual then within the aquifer itself, but it should remain in its stable form, like a solid form, for a long time. So I think it's more an issue of clogging as opposed to any other factors there. But yeah, we're looking at that, and I don't have an answer exactly yet, but I expect it to be okay for this bedrock aquifer.
Great, Bruce. Thank you so much. Great work on that project. Big challenge there. So with that, you can reach out to Bruce with his contact info on the screen. And with that, we'll move on to our next presenter.
Yep, thank you.
Our next presenter is Elizabeth Murray with Earthmaster Environmental. Liz, you should have a link on your screen to share your desktop. Did it show up?
Let's see.
There we go. Yep. Okay. So
Are we good?
we're speaking to us on in situ salt remediation, carbon and cost benefits of treating soil in place. Over to you, Liz.
Great. Thank you, everyone. So my name is Liz. I'm talking to you today about in situ salt remediation. And just a little bit about the company I work for. So Earthmaster is based in Calgary, and we're just a general services environmental company. We do have an in-house lab facility for microbiology research and for growing plants, so that allows us to do some of the experimental work that we've been involved in. So basically, what we have is a phytoremediation system that we're doing commercial applications for, but also some research and development work around. So we use a combination of plants and bacteria to remediate contaminants in soil in an eco-friendly way. So I'm going to talk to you today about in situ remediation, or managing contaminants in place. And the advantages to doing that are that it conserves the soil, it doesn't transfer the liability from the site to the landfill, and it can involve several things like adding contaminants or adding components to soil to break things down, that sort of thing. It can be more cost effective as well. I'm going to talk to you today about in situ treatment of a high salinity site. And of course, as everyone knows, the problem with salinity is that it creates problems for the plants. They have a difficult time growing, and they have a difficult time taking up water. Can't break the salts down to non-toxic components like you can with hydrocarbons. And if you don't remove the salt, then there's a potential it's going to come back and create some problems. So what are the options for remediating salt in soil? Well, the standard go-to option, I think, is remove the soil and place it in the landfill. But if you want to treat it in place, what can you do? Well, you can bind it with commercial soil binders so that it doesn't become available. You can wash it out, and that can be using components that you add to the soil or just flushing it. And you can use a couple other technologies, one being electrokinetics, the other being phytoremediation. We're a phytoremediation company, so that's the one I'm going to focus on, but I'll take you through some of the others. So the site that I'm going to talk about today is a site in southern Saskatchewan, and it had 48,000 square meters of salt impacted soil that was affecting vegetation growth. The salts went down to about 6 meters below ground level, and there had been numerous things tried on this site to try and get the site to revegetate. A groundwater system was installed in around 1997, but many large bare areas remained, and it was really difficult to get it back to usable land. And you could just see the laboratory breakdown there of the soil. So it was really quite impacted in places. And that's what some of the vegetation growth looked like that was on the site. So what if you were to landfill this site and then backfill it? Obviously, it's the quick and easy solution. The distance to the nearest landfill in this particular location was about 100 kilometers. So if you tried to landfill the total amount of soil in the site, which ended up being 288,000 cubic meters, or over 500,000 tons, the cost was going to be somewhere around $18 million, which is pretty significant. If you were to just landfill the upper 1 meter so that you could replace it and get vegetation growth, then you're looking at about $3 million to do that. So in this particular case, the landfilling wasn't feasible and it wasn't practical. So what if you were to use a soil salt binder in this site? So what those do is they permanently bind salts so that they can no longer interact. It doesn't remove the chloride from the soil, it just binds it up. There were a couple of products I was able to find online. I actually think this is the same product that's carried by 2 different companies. And what this product is designed to do is it is designed to bind low levels of sodium chloride contamination on agricultural land, so up to 3,000 parts per million. It's a humic acid based one, so basically what it does is it binds the ions and holds them in place. When I was looking at cost, the actual cost of the product is very low. You would have to pay probably about $1,200 US to get enough product to do this site. I don't know what the cost would be to apply it. I'm also not sure about what the depth of penetration would be for this product, or if it would migrate on the site, and if you could get regulatory closure using this product. So what if you looked at leaching or flushing, and that involves adding large volumes of a low salt water to the soil surface, and it basically dissolves the salts and moves them below the rooting ground or the rooting zone. You need good soil structure to do this. You require a lot of water over multiple applications, and you also likely need to add some sort of component to the soil such as gypsum. There is a commercial product called Bioxy, which is a soil salt binder, and what that does is it increases the mobility of the salt components. And then potentially you could add surfactants, which would also increase mobility of these components. One of the things you need to consider is you would have to reduce soil evaporation to prevent the salts from being drawn back up into the surface again. And keep in mind, in this particular case, it moves the salt. It doesn't remove it unless you're also flushing the soil and collecting the water. And I'm not sure what the cost of this particular one would be. Electrokinetic remediation is another option. It requires electrodes and low voltage power into the ground to create an electric field. And what it does is it destabilizes the bonds and it moves the ions to the corresponding electrodes. So you can get the sodium ions going to the cathode and the chloride ions going to the anode, and then you would flush them out to recover the salts. There is a company that does this out of Regina called Ground Effects, and they have a technology they call EK3. And when we looked at the cost that was provided on their website of $20 to $80 per cubic meter for this technology, then if you wanted to treat the total amount of contaminated soil on this site, which was 6 meters deep, then it would range from about $6 to $23 million to treat it using their cost estimates. If you were to look at remediating the top meter, so that was the 48,000 meters squared down to a meter, the cost would be around $1 to $4 million. And in addition, it's possible that the subsurface metal structures may cause problems on this site. So the other option is to phytoremediate it, and we have a technology that we call plant growth promoting rhizobacteria enhanced phytoremediation systems, or PEP systems. And what the technology does is it takes plant seeds and we coat bacteria on them. This is ubiquitous soil bacteria, and when the roots emerge, the plant cells will interact with the bacteria on the root system. And the bacteria provide hormones to increase plant growth, but they also provide inhibitors of the stress response. So you can overcome the plant's inhibitions of growth by providing components from the bacteria. And then when we facilitate the plant growth, we can then exploit the natural properties of plants, one being phytostimulation, where the bacteria colonizing the roots will break down hydrocarbons into non-toxic components, and phytoextraction, where the plants will naturally take up salts and metals and it'll accumulate in the above ground plant tissue. So basically what we have is a system where we add bacteria to plant seed, and this helps the plants grow in stressful conditions. So what exactly does the bacteria do? Well, we did some lab studies to have a look at that, working with some produced water, and you can see the two types of produced water that we use in that table there. And essentially what we do is we take different species of seeds, we try them out, plus or minus PGPR. Sometimes we add other additives, such as other hormones. And then we'll look at how these seeds germinate in Petri dishes with varying concentrations of produced water. And when you look at those germination studies, you can see a lot about what the bacteria actually provide to the seeds and to the plants. So plants will naturally accumulate salts, as I mentioned. There's two ways they do that. They hyperaccumulate, where they store the salt in their above ground plant tissue. They will also excrete, where they have little salt glands, and they'll accumulate the salts and then put them on the external parts of the plant. We work with hyperaccumulators because if you work with the excreter version, then when it rains, all that salt that's on the outside of the plants will get washed back into the soil. So we focus on working with hyperaccumulators. So how do we get them to grow in elevated salt conditions when toxicity is a problem? Well, you can see from the graphs that when you add a bacteria, you can increase the amount of germination for these seeds. And if you look at the graph on the left, you'll see I've got two different kinds of plant seeds here, an annual ryegrass and a perennial ryegrass. And if you compare the solid untreated seed to the dotted lines that represent the seed that's been treated with PGPR, and you compare the blue to the blue and the green to the green, you can see that by adding PGPR to this seed, you greatly increase the percent of germination over time. So the bacteria facilitate germination in this case. And if you look at the chart on the right, this is lethal concentration as a milligram per liter concentration of chloride. And when you look at untreated seed, which is in the hatched bars, and you compare it to the corresponding solid bar, which is a treated seed, you can see that the treated seed is able to tolerate a much higher concentration of chloride than the untreated seed. So the bacteria will increase tolerance to the salts in the produced water. Now, if you look at this data, it's a bigger picture of what's actually going on. This is LC50 again, of the two different types of produced water that I have, additional seed types here. And when you look at the percent change that the bacteria offer, on average, you can get, in this particular case, a 75% increase in tolerance to the salts in the produced water. And in this particular case, it's a 34%. So depending on the seed type and depending on what's in the produced water that you use, you can increase the tolerance of the plants quite a bit. Okay, so you've increased the tolerance. What does that actually mean when you grow them in the field? And this slide is some preliminary work that was done with our academic collaborator, the University of Waterloo. And they had two different types of soil here, a medium salt soil and a high salt soil. And they looked at growing seeds in the soil, plus and minus bacteria. And basically what this particular slide shows is that it doesn't matter how much salt is in the soil, and it doesn't really matter what plants you're growing. The plants have a finite capacity to take up sodium and chloride. So if you can't get more salt into the plant, then what benefit do you have adding bacteria to it? Well, what you can do is increase biomass. And when it comes to remediating using plants, it's all about the biomass. And when you look at the chart on the bottom, you can see that by treating with PGPR in the light green boxes here, you increase the amount of biomass on the site. Increasing the amount of biomass increases the amount of salt that you can accumulate in those plant tissues, which increases remediation. So back to our Saskatchewan site. Now keep in mind that if we were going to remediate the total depth of this site, we have to go down to 6 meters, which can be a bit of a challenge. And when we look at these sites, we look at how are we going to remove the salt from this site. When you're working with hydrocarbons, you break down the components into non-toxic components, and they are left in the soil. When you look at salts, you have to remove those salts from the site. And this is the difference between treating hydrocarbon versus salt sites with phytoremediation. So on the left-hand side, when you're working with hydrocarbons, you break down those molecules to non-toxic components and you incorporate the plants into the soil and you leave everything there. When you're working with salts, you have to remove the salts, which means you have to remove the above ground plant tissue because that's where the salts are accumulating. And we do that using standard agricultural techniques. And so that's what we did on this site. We had to harvest the above ground plant tissue in order to get rid of the salt. Now, in this particular case, we weren't expected to remediate the salt down to 6 meters. The goal was to revegetate the site to at least 70% of background levels. We wanted to reduce soil salt levels over time to allow for sustainable plant growth. So by removing the above ground plant tissue every year, we could reduce the soil levels of the salts over time to keep that plant growing. In this particular site, there were 4 types of seeds that were used: annual ryegrass, perennial ryegrass, oats, and tall wheatgrass. And that's a bacteria that was coated on the seed. So we were involved in this project for 3 growing seasons. And this is how we prepared the site. There was deep cultivation to break up the hard pan, and then some calcium amendments were added to the site. And then we added straw to increase the porosity of the soil and to hold on to some of the moisture. And then we planted, and this is what we got after 3 months of seeding. And then, of course, to remove the salts, we had to remove the above ground plant tissue, and that was done using standard agricultural techniques. And then this is what this site looked in year 3 before we were finished with this site. Now, one of the questions we have with phytoremediation is what happens when you walk away from the site? You don't want to have to continually be adding bacteria and new seed to this site. What happens if you leave it? Well, Kent Cryer, one of our field experts, happened to be going by the site a few years ago, and he was able to take a look and see how the plant growth was doing. So even though we hadn't been involved in this site for over 4 years, we were still seeing excellent growth on this site. So once you walk away from these sites, they are sustainable and you're able to maintain the growth on these sites. So what did it cost? So the phytoremediation costs were about $200,000 over 3 years, and the site was revegetated at a cost of about $4 per square meter. All previous revegetation attempts had been unsuccessful. And due to the depth of contamination, it wasn't feasible to landfill this site. One of the benefits, of course, from working with plants is that you are able to sequester carbon emissions, which can be a real benefit to companies when they're looking at their carbon footprint. And if you can remediate these sites where you've greatly reduced the carbon emissions from the work that you're doing, or you can actually get a net neutral or net negative carbon emissions from doing remediation work, then that's also a bonus. In this particular case, if you look at the chart on the right, we calculated how much emissions there were from the equipment, and then we looked at how much sequestration there was by the grasses. And over time, you can see that all of the sequestration from the grasses was able to offset what was generated from the equipment and an additional 35% on top of that. So there was a big bonus from the carbon emissions perspective to keeping the grasses on this site over the 3 years of the project and reducing the carbon emissions that way. So when you look at phytoremediation from a larger perspective and the carbon emission benefits it offers, using published values in the literature and comparing the amounts emitted by the equipment to what the grasses were able to sequester, when you subtract that from what the equipment was emitting, and you compare that to what would have been emitted when you truck this stuff to the nearest landfill, you can see, depending on the amount of cubic meters of soil that you're remediating along the bottom here, the emissions from landfilling are significantly more than if you were to phytoremediate the particular contaminant. And a lot of these sites are hydrocarbon contaminants. This was the one that we were just talking about with the salt remediation. So there's a huge advantage from a carbon emissions perspective to phytoremediating or treating in place these particular contaminants. And if you happen to just look at hydrocarbon contamination and the remediation of that, and look at the cost, you can see there's quite a significant cost to treating in place as well. And this, once again, compares landfilling to phytoremediating in place. The first one on the left here is our salt site. The rest are hydrocarbon contamination sites. And the one on the end actually has to be, is one that's up in the Northwest Territories. And you can see that there is quite a significant economic advantage to treating in place and avoiding having to go to the landfill. And for hydrocarbon contamination, certainly if you look at other alternatives, then you can see it's also significant cost benefit when you compare to other technologies. What happens if you wanted to use native species? Can you use phytoremediation using native species? One of the problems with trying to get native species established, especially in challenging conditions where there's maybe naturally high occurring salt levels, is it's tough to get native species established. And often these sites, when they get reclaimed, they're poor quality soil and they're lacking topsoil or organics. So can you apply this technology? Can you coat these particular species with bacteria, and does that help? And this is the results from a small laboratory study we did where we had soil with an elevated salinity. We were looking at blue grama grass plugs. We were actually injecting a liquid bacteria right into the plugs and then growing them. And what we found is at the higher levels of injection that we were getting significant better growth when we were able to add bacteria to these native grass plugs. So it looks like we will be able to use native grasses in high salinity areas and get some significant benefits to treating those with bacteria. Well, what happens if you have somewhat clean soil, but you know you're going to be exposing it to high salinity amounts going forward? Well, this is a commercial site down in Turner Valley, and the owner of the site, it's a brewery, they wanted to revegetate this site, and it was a commercial site that had very poor quality subsoil. It was highly compacted. It was really difficult to revegetate, and we needed to put something in here that would be able to tolerate getting continually exposed to slightly elevated salinities that would accumulate over time. In this particular case, the owner had a reverse osmosis water system, and you can see storage tank in the back here. They were accumulating the waste material from the reverse osmosis system, and they wanted to be able to use it on site to irrigate the grass they were putting in there. One, to have a more sustainable brewing process and reduce their waste and not burden the town's municipal waste system with their water waste. And two, it was just made more sense to try and use it on site and irrigate that area that we were attempting to re-veg. So that's what this site looked like. We did get it revegetated. We were using a salt-tolerant bacteria grass combination, and 25 weeks after planting that seed, we were able to get establishment of the plants. And that's what this site looked like this year. So as long as the owner continues to harvest the above ground plant tissue on this site, basically mow it and collect the cuttings, then they can continue to irrigate with these the low salinity waste that they're generating, and not eventually end up creating a wasteland where this grass is not going to grow anymore. So it's a way to offer the owner an opportunity to use the waste and be able to collect the clippings and keep it at a controllable level in the soil. So salt removal overall by plants, we're looking at an annual EC decrease of 1 to 2 decisiemens per meter. And as I mentioned, it's all about biomass. The amount of salt and chloride that the plants are able to uptake is set. If you can get more biomass per meter squared on the site, you can get more salt removal. Generally, what you see is that you get about 150 kilograms per hectare removal by using plants. So what happens if you have contaminants below the 1 meter of the rooting depth? This is how we do that. We actually phytoremediate subsoil in lifts, and this happens to be a hydrocarbon site, this picture on the right. But what we'll do is often when we're working with sites, we'll dig up the remediation if it's quite deep, and we'll place it in a treatment area, and then we'll plant the top. And as you remediate the top and the soil meets guideline values, you can strip that off, and then you'll remediate the layer underneath, and you'll continue to do that until you're through the whole layer of the soil. And that's generally how we address those deeper contaminants. So you are able to phytoremediate deeper contaminants. It just takes a little bit more time because you're treating in lifts. So what are the advantages to using a plant system? Well, it's environmentally responsible, it's green technology, the soil is conserved and reused, it's not disposed in a landfill, you're not moving the liability to another location. It's especially suitable for remote locations, especially those in the north. We actually get really good growth up north with the long days that they have in the growing season. Phytoremediation is especially effective for challenging contaminants for hydrocarbon fractions F3 and F4. And for those that you can't remove or are difficult to remove from the soil, such as salts and metals, because you can't actually remove them using plants. And of course, the economic advantages, it's low cost compared to other technologies. And the cost can be spread over several years, so you're not all at once paying for the full cost of the technology. So what's the next steps for us? We're always looking for new bacteria for new applications. So we do this in the lab here in-house. We're looking at isolating new bacteria, trying them with different contaminants, and see if we can get other applications where phytoremediation can be a fairly user-friendly and effective way to treat other contaminants. And then in the non-remediation related field, we also have been involved in some reclamation work this year with the City of Calgary. And this was a site in the northeast of Calgary along 16th Avenue where we were working with the city to replace the Kentucky bluegrass or the agronomic grasses on the roadsides in that area and replace them with a series of annual and perennial wildflowers. And so this is one of the fun projects that we get to do outside of the remediation world. And it was actually quite a fun project to work on this year. So I just want to finish by now acknowledging the National Research Council of Canada and their Industrial Research Assistance Program. They've provided funding for some of this work. And I also want to thank the clients that have helped us do some field trials for the PEP systems technology. We do a lot of hydrocarbon remediation and some salt remediation, but the clients have been great about allowing us to try some different things. So I want to thank you for listening to my talk today, and I'd be happy to answer any questions you might have.
Thanks, Liz. It looks like we have a few questions for you. And one that someone else is asking the same question I had. In the first case study, what was done with the harvested bales?
Yeah, we get that question a lot. So often when we're using these technologies up north, the critters will eat the grass and there really isn't an opportunity to harvest it. And they go off and deposit the outcomes of eating grass in other locations. This particular site, when we're harvesting it, it's up to the client what they want done with the grasses, and often the clients don't want it to be used for livestock feed or something like that. Often what happens is it ends up being used to line truck boxes in the winter for soil that's going to the landfill. So it does get landfilled. It is non-toxic. Bruce Greenberg's group at the University of Waterloo, our collaborators have done the work on that. The salt levels are not toxic. They're low levels because obviously if they were toxic, the plants would die. So it's quite acceptable for critters to eat this material, but the clients tend not to want the material used for that.
Okay, for the brewery project, what can be done with the grass clippings that are removed? Can they go into the compost program or do they need to be landfilled?
You know, I don't know what he's doing with them. I'm assuming he's throwing them in the waste, but I guess if he has a compost area, the amount of salinity in this water is really low. It would take a really long time to up the amounts that it would create some significant problems. So I'm guessing, knowing Jochen, I'm guessing that he's probably composting them.
Okay. Since you're leaving the site as an improved pasture, how have you considered adding a deep-rooted species such as dryland alfalfa to seed mix to try to remove some of the deeper salinity?
Yeah, we've actually done some work with alfalfa. We did some work up in the Sundre area with alfalfa. The species that are there are totally up to the landowner. We haven't been involved in that site for, well, probably about 8 years now, and it's whatever they want to put there, but certainly deeper rooted species mixed in with the high biomass species is the way to go to reach the deeper contamination for sure.
Okay. And then we had what happens to, just a repeat of what happens to the grass that is harvested from a remediation site.
Yeah, and as I mentioned, if we're remediating hydrocarbons, that grass just gets left in site and it gets plowed under to add organics to the soil, because we're normally dealing with poor quality subsoil. They really could benefit from the addition of some organics, so that grass just gets plowed under.
Okay. Great. If anyone has any other questions, please reach out to Liz over at Earthmaster Environmental. Again, just a reminder, the video will be available later today or first thing tomorrow, along with links to the presentation. So with that, thanks, Liz, and we'll move on to our fourth presentation this morning and the one right before our break. I'm going to share. Next up is Victoria Collins from NATE. Victoria, you should see a link on your screen to share your desktop and your presentation. And Victoria is going to be speaking about bugs and veggies, optimization of plant-based dewatering and deployment of technology for fluid tailings.
Okay. Can you just let me know if I'm sharing the right screen?
We can see your browser.
All right.
There you go.
Is that better?
Yeah, now presentation mode will all be good.
Perfect.
Okay,
Are you getting the right?
That's up, yeah. Swap view, yeah. Click and then swap. Perfect. Thank you.
Excellent. Thank you. Yeah, so I'm going to be talking about our project called Bugs and Veggies today. It's a project where we're utilizing plants to dewater oil sand tailings. My name is Victoria. I'm NATE's resident microbiologist, and if you have any additional questions after the end of this presentation, please feel free to email me. That's my email in the bottom corner there. All right, so I'm going to give you a little bit of background. Probably everybody knows about oil sand tailings, so my apologies if this is really redundant for you. I'll just give a little bit of background for anyone who might not be as familiar. So oil sand tailings are formed from open pit mining. This is where topsoil and overburden are stripped away and a traditional top-down mine is formed. Bitumen ores are then recovered and they're processed to extract the bitumen. This involves treating them with water and caustics, grinding up the ores, and at the end of this process, the bitumen has been recovered and the slurry is formed. The slurry is then pumped out to tailings ponds where it's left to settle and densify. The water is then recycled from this material and used back in the tailings or the bitumen extraction process. So once it's in the ponds, the tailings are composed predominantly of water, sand, silt, and clay, along with some residual bitumen, but really the majority of that material is water. The problem with tailings isn't just that we have this big pond of mud, it's that the clay particles in this pond have really, really high affinity for water. So the water basically forms a little shell around every single clay particle, and that stops those clay particles from interacting. And because of that, they can't settle. They just stay in this suspension. After the material has sat for about a decade or so, it'll reach about 30% solids content, and it doesn't really get any more solid than that. So it forms this stable suspension. And this can go on for decades. We're not actually sure how long it would take to settle out naturally. In untreated tailings, we're looking at solids content between 10 and 30%. Again, 30% is still after about a decade of settling. On treated tailings, this is using treatments like thickened tailings, so additions of polymer or gypsum, centrifuging. It can also go through freeze-thaw cycling, but we tend to cap out at around 60% solids and insufficient shear strength to be considered trafficable, meaning being able to walk and drive on this material. So because of these challenges, we've accumulated a total volume of about 1.24 billion cubic meters. which is an immense amount of tailings. So the problem with oil sand tailings isn't really that we have this waste product or that the waste product is toxic or any of these other things we might hear about tailings. The biggest issue really is the volume and how to address that volume in a way that's cost effective. One of the things that we've been looking at is plant-mediated tailings dewatering. This has been this has been an area of interest for researchers on and off over the last 2 decades, but it's never really gotten past the greenhouse phase. So plants can be used to dewater tailings in theory because plant roots are really good at liberating water from soils. And because they can draw this water up from the soils, they're exerting these pressures like capillary forces that cause the water to come up from even deeper so it can be accessed by the roots. The water is then released to the environment through evapotranspiration. So we have since seen tailings or plant species used for tailings pond bank stabilization, so for civil engineering purposes, and they've been looked at again for dewatering. But all of these studies that have been looked at previously are using non-native plant species, so plants from other areas of the world and potentially modified plant species. And the oil sand operators really are under a mandate to try and use native species as much as possible in this work. So some of the factors that we found will negatively impact the growth of plants in general, as well as our native species especially, are the highly saline conditions that we have in tailings. There's also limited nutrients, so these are things like nitrogen and phosphorus that plants need to survive. And then also sometimes you have contaminating hydrocarbons or organic acids like naphthenic acids, and those can negatively impact plant growth as well. That being said, NATE does have an ongoing study on a tailings closure cell where we planted a bunch of upland species. These are predominantly grasses back in 2017. In 2018, they were doing okay around the edges, but we ended up with a flood that wiped out a lot of the plant species growing there. And then in very early 2019, we planted wetland species. And you can see in that last picture there, the 2019, by the end of that season, they were doing fairly well. So we do know that plants can survive there. They're just a little bit more sensitive and they take a little bit longer to grow. So one of the things we wanted to look at was bioaugmentation and then also biostimulation to help promote plant growth. Bioaugmentation is the addition of bacteria, whereas biostimulation is the addition of nutrients. So in several studies, they've found that adding microorganisms, as we've just learned about in our previous presentation here, they can promote plant growth, they can degrade plant stress hormones or produce plant growth hormones, and they can also assist in biodegradation of organic contaminants or sequestering of contaminants away from the plants. This has been used a lot in agriculture, assisting in things like seed germination and yield, increasing nutrient content, but we've also seen it used in phytoremediation. And I know we just saw a presentation on that, so this picture is less good, but I do have this picture here, just a study out of the University of Washington. They were using poplars to remediate trichloroethylene, which is TCE, and they had plant growth promoting bacteria added to some plants and not to others. So that's the yellow bars there are showing the height of those trees, those poplars, where plant growth promoting bacteria were added, whereas the red lines you can see are the height of the trees where they weren't treated with these plant growth promoting bacteria. So there can be a significant effect. In our previous work, our original bugs and veggies work, we were looking at just growing these plants on tailings to see if we could get these particular native plant species growing outdoors in our tailings columns. Our columns were about 1 meter tall and 10 centimeters wide. We used thickened tailings and centrifuge cake. So these are about 60% solids content. And we added for our organic amendments were peat and hydrochar. Everyone's familiar with peat, I'm sure, but hydrochar is, it's a proteinaceous nutrient. So what we do is we have meat and bone meal and we do a water extraction, and then we hydrolyze the water and the proteins collected in that water through using a hydrolysis reactor. And that's where this material is exposed to high temperature and high pressure, and it causes these proteins to be cleaved up into little bite-sized pieces that bacteria and plants are able to utilize. We also added tailings that were bacteria, sorry, that were enriched from oil sand tailings, and these were enriched to fix nitrogen. And this is one of the treatments we were looking at to potentially help overcome nitrogen deficiency in the longer term. And the columns, again, were grown outside. They were grown for 3.5 months or so until the columns had dried down substantially. At the end of this study, we found that on average, willows improved consolidation by about 5.3 centimeters, which is 58%, and decreased water levels by about 24% compared to the non-vegetated columns. So we found basically that we had a huge effect from adding these willows to our tailings columns. We didn't see any effect really from the slender wheatgrass that we added, and that's because the seeds got trapped in a crust that formed on the surface really quickly. We do get crusting over tailings in general, but in these small columns, only about 10 centimeters, the crust can form quite quick. So because we had added seeds to the top, they were trapped and they weren't able to grow very well. We did reseed them, but we still weren't able to grow them for long enough to get a substantial effect. That being said, our willows did really well. That's me holding a plug that I pulled out of one of the willow columns. So I was actually able to grab it by the top and just pick it up, straight up, and that's the amount of material that came out with it. So it's about 80 centimeters, or basically the whole column there. You can see it's really solid at the top and then really soupy at the bottom. We found that throughout that top part, we had substantial increases in solid content, but we had significant improvement in shear strength throughout the entirety of the column. And that's because we had all of those roots at the bottom holding together that tailings material in the same way that we would use rebar to hold together cement. So, concrete. So as far as our treatments went, we found that hydrochar increased the leaf biomass, which increased shear strength. And that's because of that leaf biomass was also correlated to improved root biomass. So the more roots we had, the better the shear strength. The bacteria were found to improve that root biomass, and when the two of them were combined, we had a much higher shear strength than any of the other treatments or than hydrochar alone. And so we were really interested in continuing with our bacteria work to see if we could optimize it and to continue evaluating hydrochar in this application. So one of the downsides to that previous study was that we were dealing with tailings with relatively high solids content, again around 60%. But the majority of our legacy tailings that we have to address are around 30% or lower solids content. And so you can't actually put a plant on top of this material and have it stay there. So we wanted to optimize our deployment method while continuing to look at our different treatments. What we wanted to do was use these vegetated floating mats as a progressive tailings dewatering strategy, where we could launch these mats out on a closure cell and have wetland species remove the surface water and increase the solids content in the upper layers so that our flood tolerant upland species, so the willow that we've been looking at, would be able to send its roots down and be able to dewater at depth. So to optimize this process, we broke it into 2 phases. The first phase was all optimization and the second phase is scale up. This was broken down into a few trials. In the first one, we wanted to make sure that our selection of plant species would be able to grow well together. It shouldn't have been an issue, but every now and again, you get these allelopathic effects where some plants just don't like growing next to other plants. In our trial 2, we also wanted to optimize the floating mat material. This is really to make sure that it can support the vegetation, that it's able to stay floating, and ideally that we'd be able to promote the growth of particular plants in there. In trial 3, we looked at different amendments. We did a factorial study looking at fertilizer and hydrochar, and then we evaluated a bunch of different bacteria and fungi to see if any of them would have a positive impact on promoting their growth in tailings. So in trial 1, we looked at water sedge, which is Carex equatalis. We looked at Rumix occidentalis, which is Western dock. That's a little bit more of a transitional species. You can find it between wetlands and uplands. And then we looked at Salix interior, which is sambar willow, and that's our flood-tolerant upland species. In general, it wasn't a big shock, our results here. This is showing our above-ground biomass. In general, everything performed relatively well. The plants didn't mind too much growing in combination with one another. We did see a little bit of a decrease in plant growth in Rumix when it was grown. Well, we saw, I guess, an increase in Rumix growth when it was grown with Carex because it really liked Carex for some reason. But in the rest of the studies, we saw nothing, no adverse effects. So we were able to move forward with those 3 plant species we had selected. And just if you're wondering, that first study was run for about 30 days only. On the second phase here, we looked at 3 different floating mat materials. The first one, barrel 1, we used this really thin mat. It's made out of similar to what you would use on your gym floor, those big puzzle pieces you can get, or in a garage or a play area. And then holes were put in these, and little baskets to suspend the plants in the tailings material were inserted into those holes. In the second barrel, we used what we're calling the biodegradable mats. This was put together by our collaborators in Center for Boreal Research, and they made this out of coconut coir and a little bit of mesh and some willow branches to see if we can keep that afloat and use that material. And then in our third barrel, we used what we're calling the thick mat. It's about 5 inches thick, and it's this woven mesh. So it's porous, so water can infiltrate and roots can infiltrate around where the plugs would be put. But yeah, it's a very thick plastic mesh. At the beginning of this study, we had about 32% solids content in those tailings, so that's why it looks so fluid. And then this was grown for about 15 weeks. So this is just a top-down view of all 3 of the barrels. From this angle, they all look about the same, but you can see that we had like really nice growth of these native species. This is our barrel 1. That first picture, it's again, really floppy, so it's not a great picture, but we have a decent sized willow kind of hanging down from the top there. The second picture shows just the tailings material. This is what it looked like after we lifted that mat up. And the third image just shows the roots dangling down through those little cups. Some pictures of our second mat, the biodegradable mat. You can't see as much vegetation here in the first picture. In the second one there, you can see a part of our mat was left behind in the tailings, but otherwise the tailings look about the same. And then again, you can see roots coming down in the third picture. But in barrel 3 with our thick mat, if you look at that first picture there, you can see we have an immense willow growing out of it. This willow was well over 1 meter tall, and it just blew us away with how very tall that the willow was. So I guess it really enjoyed this particular mat material. The rest of it looks about the same. In the end, our tailings content, solids content of the tailings in all of them had reached between 56 and 60%. So here's our data showing the biomass. It just says 1, 2, 3. That's the barrels 1, 2, and 3. In the third barrel, so the thick mat barrel, we only had 3 willows growing there. All of the other barrels had 4 willows that had been planted, but we had 1 willow that had just died right at the very beginning. The seedling was kind of a dud, but in general, like the rest of the plants were all the same. We all had four of every plant in all of them other than that. Taking this into account, you can see that this last section here, again, the salix, has more biomass than the salix growing in any of the other mats. And we thought that was really cool considering it's 1 plant fewer. The rumex also did considerably well, and the carex did a little bit less well than in the other 2. And we think this is because this larger mat allowed for greater root aeration. And because salix is an upland species and rumex is a transitional species, they both enjoyed having more oxygen access to the roots, whereas carex is a dedicated aquatic species and prefers to have the roots totally submerged in water. When we looked at the overall biomass, we did find that there was significant improvement in our third barrel there with the thick mat, and so this is the one that we decided to move forward with. Finally, we were looking at amendments. So this is where we are looking at, we did a fully factorial study where we looked at hydrochar and fertilizer in combination, as well as 4 different microbial amendments and their controls. These were set up using just 2 plant species in 10-liter pails, and we only used these two species instead of the 3 we were looking at because we couldn't really easily fit the 3rd species into those pails. And so we chose to go with the salix and the carex because the microorganisms we were adding were more likely to affiliate with these plant species. So if we were going to see some successful results from that, then we anticipated we'd be more likely to see it with these particular plants. These were only grown for about 6 weeks in the pails. there was an issue where too many people were on vacation at the same time, and so they neglected to water it for about a week, and so we had to truncate the study about 2 weeks early. From this study, we measured above and below ground biomass. We looked at micro and macronutrients, as well as nitrogen in plants. And then we did a microbial characterization of the roots and the root-associated tailings material. This one. So this is some data just showing our biomass. This is the above ground biomass. We weren't able to measure the roots because they had dried the material down so much that it was basically roots bound in clay pucks. This is showing our the differences between our different microbial treatments. So it's the B1 through 5, and I have a legend there at the bottom if you're interested. We didn't really see a significant result or a significant difference between any of our microbial amended treatments. And we're all very disappointed by this, but we think that it's because we didn't allow those plants enough time to grow in conjunction with these microbial amendments. And so they weren't given enough time to fully colonize the roots and be able to have an effect. So it was unfortunate, but we're looking still at the microbial community. We recently got that data, and so we're picking through it right now to see if any of them had strongly associated with the roots, but maybe not showing an effect on plant growth yet. So we're still picking through that data. We also added hydrochar and hydrochar fertilizer combinations. And again, here you can see the amazing result. Fertilizer promotes plant growth. No one saw it coming. But so we didn't see a significant effect from the hydrochar in and of itself. But if you look closely at it, you'll see that when you compare hydrochar with none in both of the carex and the willow, you see the hydrochar is on average a little bit higher. And even hydrochar with fertilizer and fertilizer alone, we see a little bit more biomass development in our hydrochar, in the treatments that have hydrochar added. And when we were looking at our microbial analysis, we did find that adding hydrochar to the tailings material resulted in a totally different microbial community than when we just had the plants growing in the tailings with fertilizer. And the community that tended to promote were microbial groups associated with promoting plant growth. So things like we have some Pseudomonas and bacilli that we know, species that we know have been previously found to promote plant growth. So we're really interested in moving forward with that work. And it's kind of a benefit because the hydrochar is a lot easier to add. It's a treatment that could be added in line. It's liquid, it stays in suspension. And so it would be really easy to add to a closure cell with minimal mineral prep required. Whereas adding a microbial amendment will be a little bit more difficult. We either have to source it commercially or grow it ourselves. And it requires a little bit more work there. So for the next part of this work, we're moving forward with the hydrochar and fertilizer combinations. And in our scale up here, we're, like I said, we're going to be moving forward with 3 different treatments and our controls. So our 3 treatments that we're going to be looking at in this next phase of the work is adding fertilizer, fertilizer plus hydrochar, hydrochar alone, and then some evaporation controls. This is already set up, and it's set up in 300-liter, I'm showing barrels here, but they're actually giant tubs. These are 2 feet or 2.5 feet-ish by 2 feet by 4 feet. And we have 4 replicates of these that will be grown indoors for 6 months. And the reason we're looking at 6 months is because this simulates roughly 2 growing seasons outdoors. So hydrochar is being added to some of these treatments, and we're going to be looking at the microbial community and seeing how those microbes might be affected and how that plant growth is going to be affected with that longer growing time. We're also going to be looking at microbial function here. So we're going to be seeing what kind of gene expression what kind of gene expression exists for plant growth promoting genes in the bacteria associating with the roots by the end of this study. And of course, we're going to be looking at shear strength and solids content because the primary objective of this work is to produce trafficable materials, and then biomass to determine how well those plants actually grow on the material. Something else that I don't have in this picture here, I have a little arrow going right to field trials after this, but we're actually going to be scaling this up one further through a project extension and looking at deploying these mats on totes of tailings. So this is going to be about 1,000 liters. So we actually have everything already prepped to go on that. And once we have the results from this particular phase of work, we're going to be able to take our award-winning treatment and put it on those totes and see what happens. So the applications for this work it's largely like you wouldn't put this out on a tailings pond. This is for tailings closure cells. So when tailings material has been selected for reclamation and they want to get rid of a certain volume of tailings, we'd be using this floating mat technology to potentially as a capping technology where it could be deployed on the surface and substantially increase that shear strength so that reclamation material can go over top. So this would be then covered in sand and mineral mix and topsoil so that it could actually be reclaimed into upland landscape. Or we could be using it for dewatering and lifts where a 1 to 3 meter lift is poured into a closure cell, and then these mats are deployed, and then additional meters are added on top of that. And we'd still need to do a few studies to determine if we'd have to launch new mats every time, or if these plants, which have all been selected for their ability to sucker and form new plants, we'd have to find out if we need to plant new or if those plants would be able to persist throughout the lifts. Yeah, so that's our end goal, our end hope for this project. And in general, I'd like to acknowledge everyone who's worked on this. We have our colleagues up at the Center for Boreal Research. They've taken care of most of the greenhouse work. Lots of lab technicians. My Commander-in-Chief, Paolo Massone from Clean Technologies at NATE. Our industry steward, Gavin Freeman from Canadian Natural. And the many students and staff who have had a hand in this. More recently, Caitlin Grado has been awesome. She helped us carry a lot of tailings, chip through frozen tailings, and do a lot of heavy lifting. Yeah, so thanks, and please let me know if you have any questions.
Thank you, Victoria. The first question is your goal to completely enclose the ponds at some point in the future?
It wouldn't be the entirety of the tailings ponds. This is really a technology that aims at targeting closure cells. So the ponds are predominantly still active, so water and materials are still being put into them. And when tailings are reclaimed, it's reclaimed in one closure cell at a time. So if they end up wanting to reclaim an entire tailings pond, and they want to do it at once, they'll probably be looking at more of a wet landscape reclamation where they can turn it into an end pit lake. But for dry landscape, it's done in smaller volumes to make sure that we're able to address the water issue. I'm not sure if you're aware, but for dry landscape reclamation, the way that it is reclaimed, once you have it's forested and everything, it has to be guaranteed not to sink more than half a meter over the course of time. So they have to reclaim these smaller pockets of tailing closure cells because they wouldn't be able to accomplish that on a larger lake.
Right. What has the various regulators' response been to this research?
So far, people have been pretty excited. There hasn't been, we haven't approached the regulator as trying to actually deploy this technology on cells just yet because we're still optimizing this laboratory phase. But we do have a few people who are watching this work from the Alberta energy regulators and who are interested in its progression.
Great, great presentation, and thank you again, Victoria. Thank you to our first batch of presenters, Paul, Bruce, Elizabeth, and Victoria. We will take a short 15-minute break. Everyone can stretch their legs, grab a coffee, and then we'll come back for our final 4 presentations. No need to leave the webinar, though you might hear me getting the next presenters ready, but we'll see you back here at 10:45. Thank you. Hey, Bud, I just shared the link with you to share your presentation.
Hi, Joe. Okay, I'll just bring it up and get the slide set until you give me the green light to go, okay?
Yeah, yeah.
Thanks, pal. Oh, hang on there. Okay.
Perfect, perfect. We'll leave it like, just leave it like that, and I'll be back in, everyone will get started in 4 minutes.
Okay, I'll drink some coffee and wait.
So I think Bud needs more caffeine.
Thanks, pal.
Welcome back, everybody. Just a reminder, today's webinar is sponsored by Abacus Enterprises. Later today, you'll also, or tomorrow, you'll receive a link to the video of this entire webinar, as long as a link to the webinar from last week, and along with the link to the presentations. Our next presenter is Bud Ivy, George Bud Ivy from Ivy International, out on the wet coast. Hopefully Bud's dry. Bud's going to be speaking on sustainable surfactant enhanced aquifer remediation combined with multi-phase extraction of coal tar, L-NAPL, D-NAPL impacted brownfield sites. you could have made that a little longer for me, bud.
I'll try to. I know you like reading long titles, so I just try to keep that up, right? So.
Well, it checks my reading and skills. So over to you, bud. Thanks for presenting today.
Yeah, thanks for organizing this, Joe, and doing, as you call it, the RemTech of a number of the presentations from RemTech. I think that's great to give people greater access to the event. So I'm going to hit my timer now for my presentation. And yeah, so I'd like to thank everybody for making the time to be here today. I appreciate the opportunity to speak to you. So again, you've heard my short title about what I'm talking about. So without further ado, it's obviously related to LNAPL and DNAPL and enhanced ways of remediating that. So without further ado, I'm just going to get cranking along here. Yeah, just some nice images coming up there. Because of the way my background, for those that don't know, I'm a synthetic organic chemist, so the type of guy I jokingly say can go in the lab and make a heart drug. But I, back in the late 1980s, I went across the campus and university and did geotechnical engineering, which at the time just made me very broke. But it did open up my eyes to a broader understanding of, soil, water, ground, contaminants, so on and so forth. So it really affects the way I look at things. And I often look at sites as patients, and that we have to try to go and heal them. Not only do we heal them, we have to evaluate them as part of the medical team and then come up with some really interesting ideas to make them better. So that word healing means a lot to me. So when we're dealing with LNAPL or DNAPL contaminations, there's a lot of anthropogenic sources of contamination. And yeah, since as long as we're using these products, there can be above ground, below ground storage spills, there can be pipeline spills. We transport fuels by rail, by road, there could be spills that way. Even offshore spills or waterway spills can occur. And as we know, we typically look at these contaminants and we think of LNAPLs that float on water. If they make contact with water, they'll float. However, when they do spill on the surface, the rate at which they move through geology is a function of the grain size. Obviously, the finer the grains, the slower it's going to move. And we typically associate DNAPLs with being heavier than water, so they'll go deeper. And again, they'll get hung up on some kind of confining layer of geology. But when we're looking at the simplified view of absolute sinkers or floaters is a little bit of a misnomer in that there's a lot of compounds that actually sit in between, as that baler that I'm showing there shows. So I'll actually talk about a manufactured gas plant today that we remediated, where we had to deal with multiple phases of contamination for remediation. So the better you understand the contaminants, the better you can actually characterize them and clean them up. So non-aqueous phase liquids is just almost by virtue of their name, they don't easily dissolve in water because they don't do hydrogen bonding with it, so they tend to phase partition. So they'll absorb onto soils, and then they can build up in layers. You can see globules being formed, or in chlorinated solvents called ganglia. And that higher concentration, you'll actually see measurable floating or sinking product, right? The unfortunate part is with this phase partitioning, it reduces their availability for remediation of all forms. And again, we tend to think of LNAPLs as being floaters and the DNAPLs as being the sinkers, as I'm showing here, which is fine. But there are things that kind of tend to behave in between, something to think about, okay? The other thing happens is as these build up in these finer grain pores, they actually start to clog off flow. No different than, probably building up a plaque in your arteries. So it reduces flow. And remember that the veins in your body are much broader than the typical pathways in a lot of finer grade geology. Anyways, as they build up, they slow down the groundwater movement, and sometimes they actually bridge it off or block it off. So you get some issues there. But what really catches my interest as a chemist is to share what's actually happening at that interface between these phases and the groundwater. And we know we've got geology there. So I look at things like interfacial tension, aggregation, absorption. So it's not simply looking at pore pressure, things like this, because those comments actually fall deaf on most chemists' ears, because there's underlying factors that give rise to what you're measuring. And the better you know those, the better. I like this photo because it speaks to what I was saying before, in that there's a lot of different densities to compounds here. Lamp oil on rubbering alcohol and vegetable oil on water. There's some dish soap, milk, maple syrup, corn syrup, and even honey at the bottom. Showing there's a different phases. You've probably gone to a bar and ordered a drink, and the mixologist, the bartenders actually made your drinks have multiple layers. It's kind of fun because they're playing with density. So contaminants, and a lot of organics are here, will have a tendency of behaving in different ways. So be careful about any broad assumptions we make, because there's more going on. And when we're dealing with even vapor phase, and by the way, vapors don't care if they're in the LNAPL or DNAPL phase. They don't care about the density. They tend to be the small compounds. So they're non-aqueous phase gases. And so as much as you guys talk about LNAPL or DNAPL, well, when you have gases built up and absorbed onto soils, essentially you have that phase, a free phase of those occurring, and that can be the source of indoor vapor intrusion, which is becoming a really big, significant issue in a lot of sites. So we get back to my whole idea of geology here in brown, the groundwater in blue, green being typical contaminants, and that white being that vapor phase contamination. But again, what's going on at those contact planes between all these various phases? And in some cases, we have multiples, right? 3 to 4 or more. So it's something to think about, right? So I'm gonna kind of expand upon that and give you a slightly different view on these. And everything I'm about to say, you can actually corroborate through doing a little bit of research on your own. Now, we know that the surface tension of water is around 73 dynes, a function of temperature. And we know most of the contaminants that you're dealing with out there, petroleum hydrocarbons, chlorinated solvents, I don't care if it's PFAS, organometallics, the typical surface tension of them is around 21 to 23, plus or minus, again, a function of temperature. So we tend to see this phase partitioning occurring, but what's happening at that contact plane? So I like to use interfacial tension to talk about that. So when they come together, and the water and the oil don't tend to move past each other when they come to that contact. And again, as we know, the contaminants don't dissolve very well. But the one thing we don't hear much talked about, unless you come from a chemistry background, is let's imagine for a moment that free phase, so that NAPL, is benzene. Benzene has a low 20s surface tension. But when the benzene comes in direct contact with water and it persists for a period of time, the benzene reorganizes itself along that contact plane and the surface tension goes up into 30s to 40s. Oh, interesting. Something to think about. So it's just not really stagnant what's going on. There's actually some things taking place. So just think about that for a moment. The other thing I got to talk about is agglomeration, which really isn't the right term to use. And that's when particles come together. It's aggregation is a term that we should be looking at. And I made up a slide on that for you guys. But when these things start to stick together, that's when they form the layers, the globules, and that floating or sinking NAPL layer. So something to think about. But a way I like to look at it is something that we can relate to is when we do get this plaquing occurring in our arteries from things that we eat, and it kind of bridges off blood flow and whatnot, which could be quite harmful for you if you have any cardiac issues. But the point you want to take from this is even if we think about the same thing occurring in the subsurface, which it does, by the way, it starts to pinch off or reduce flow. And the more finer grained geology we have, which is typical of Canada, we have glaciated, it becomes an issue. It causes pathway interference, whether you're injecting, extracting, or trying to do something physical, chemical, or biological on site. So think about that. It is occurring. So here's a better term to look at agglomeration, but aggregation is what the molecules do, because like dissolves like and like attracts like. So those layers build up, forming those globules and those floating or sinking layers. And once they get agglomerated together, you have an issue for getting them off because they're less available. So something to contend with. And here just showing typical phase partitioning that occurs. That's even frac sand from Alberta, actually. There's some drill cuttings, and there's just some heavily contaminated soil from a spill. And we're dealing with sorption. Here we have some typically sorbed contamination because it's not dissolving very well. Yeah, water, contaminants dissolve in water so that none of us can drink it, and even at parts per billion or parts per trillion for some contaminants. But that's not amazing solubility compared to, say, salt or sugar, by example. So it's not really impressive, but it does phase partition. And that stuff that does absorb to the surface is less available to you. So you need to get that off that surface to make it more available for physical, chemical, and biological processes, which is what I'm talking about today. So we'll get into that. Here's a great quote that I like from 2005, talking about issues that have been in play for almost 3 decades or more that we've been paying attention to. It says, during the past decade, much discussion has centered on the unavailability of sorbed compounds to microorganisms. It is now generally assumed that desorption, diffusion of bound contaminants to the aqueous phase is required for microbial degradation. So anyone out there ever doing bioremediation on your biopile stalls, there are ways of improving desorption because the bacteria can break those compounds down. And I don't care if they're F3 and F4, they just happen to absorb a lot. So if we overcome that, we can improve it. So just talking about the issues that occur from a physical perspective, you do pump and treatment, multi-phase extraction, the contaminants are less available when they're absorbed, less available to biological, aerobic, anaerobic, or facultative processes. Chemically available, oxidation, reduction, and there's about 4 other classes of reactions that we're not currently talking about, which also get hindered by this. So it's something to think about. Absorption become a really major factor. Don't forget interfacial tension, don't forget aggregation, they all come into play. So how does IBSOL work? Myself being an organic chemist, I didn't like the idea of, if I jokingly pick on Joe and say Joe is an oil droplet and a ping pong ball is a surfactant, having to cover Joe with 500 ping pong balls, get him to float like a spaceman in the International Space Station, or that idea of being floating in those pore spaces. To me, that didn't really make sense. It'd be better if we could have an affinity for the different types of molecules that are out there, because we have a lot of different ones: gasoline, diesel, motor oil, bunker seed, the list goes on. Well, they all have certain regions or functional groups on them, just like in biochemistry, you can have an affinity for those. So that's what I wanted to do. And as you're seeing here is when we have that layer or that globule or what have you, we can lift that off without encapsulating or causing a micelle. And that image just pops up, and you're right, is how most surfactants work. That's not very selective, and the benefit of what I'm doing is a lower concentration can be very effective. And all we want to do again is overcome sorption, overcome interfacial tension, overcome aggregation to make these more available for the processes that you're typically doing now. Not bad. And because that's selectivity, we have different formulations. And then some people that are playing with PFOA, PFOS, we have another product we're calling PFAS sol that I can talk to you about. And again, because we do not have to cause emulsification, which will hinder your ability to use oil water separators and do water treatment of your wastewater, that does not become an issue with us. So again, you can dilute our product. A drum of our product would make 50 drums of diluted product for applications at site. So a little goes a long way. Now I'm going to talk about something else, because I've been talking about all these other factors. There's another factor in play. It's called water. We've all been taught in school that water is H2O. Well, that's okay, but it's really more a model of what water is. And you're all thinking, what's he talking about? Well, water, because it's polar, as I'm showing, electronegative oxygen, electropositive hydrogen, it behaves like a magnet. We've all been taught about hydrogen bonding, how one water molecules attract the next. And if you've ever done a belly flop into a swimming pool or into the river, it probably hurt your skin if you hit it, pretty head on. So what really goes on when you see this droplet of water on fine sand, by the way, what's really going on there? So what you see at the gross kind of level speaks to what's happening at the atomic or microscopic level. So water does do hydrogen bonding to its neighbor, but it does so in a three-dimensional pattern in a very organized way. And this is what you're pushing and pulling through most of your sites. It's called a water cluster. This is not a new term. It's been around for over 100 years, and a lot of people study these. And this is what you're pushing and pulling through on sites. If water was truly H2O, it would race like an F1 race car straight through all that silt and clay and all those little openings, no problem at all. Well, that's not the case. It's sluggish because of this. Now, the good part about IVSol, not only are we trying to make these Zorb phases, these globule phases, these NAPL and aggregated compounds more miscible, so they're more available, we can actually start to change the surface tension of water from, shall we say, 73 dynes down below 30. Now, remember that earlier slide I showed about that contact between the L-NAPL and some contaminant, and that was around 20 to 30, and how they can reorganize something, maybe that benzene come 40. Well, if they come very similar, even interfacial tension, which inhibits flow or contact or movement, can be overcome. So you're not just restricted by chemistry. Interesting. A good example of this is, imagine we have some absorbed or blocked off issues on sites, and this happens a lot if the contamination levels are high. Getting contact or delivery is an issue, but if we can change the size of those clusters, it allows us to work on those layers, open up those clogged pore throats, and actually start to make access. And when we get access, and then we start working on that, increasing its physical, chemical, and biological availability. And just, we're not a pump and treatment system. IVSol is not a biological package, and it's not any kind of chemical package. It's a facilitator to increase availability of things, that you can improve the availability so that you can improve remediation of those methods and others that we're currently, again, not talking about. But I'll bring up more of that in another presentation. Just showing how we take highly contaminated materials and make them less contaminated. That's actually from a refinery site in Western Canada that we did some soil washing at. So here's that interfacial tension again. Remember, 73 dynes, and maybe it's benzene over there getting into the 30s to 40s, and all of a sudden we drop the water to something down into 30s or 40s. Well, all of a sudden that interfacial tension issue is gone. We're taking things that don't want to dissolve in water and making them miscible. Wow. As I said in my presentation at RemTech, we typically think of surfactants about bringing, oils into water. You can bring water into oil, so it doesn't have to be a one-way street, it can be both. And we actually employ that mechanism, because I'm a chemist, to do both. Why rely on one when we can have both in play? So we do. So that's another unique factor of what we're trying to do. Again, all we're trying to do is increase availability of those contaminants to the methods you're employing. And another thing you can do is, you'll hear talked out in other conferences and a bit on this one, is the combination of technologies. And people are realizing there's no silver bullet. It's often a case of aggregating different technologies together to bring out a better solution for your clients, which is great. So I'm really happy to see that still occurring. And again, our objective here is to take that separated phase and making that missable to allow you guys to remediate those sites as I'm showing in those images. So now I'm going to talk about our typical application on a lot of these sites. We can do in situ and ex situ applications. Here shows like the application of vertical injection wells that can be angled, they can be horizontal. The point is you're injecting into them, the injected mixture goes out through the slots in the well, and you probably have that screened across that contamination zone. Another scenario is where maybe you have a roadway, a building, maybe a pipeline, maybe it's fiber optics, I don't know. And on one side of that, you will put in some injection wells while you're extracting at the other, and you basically sweep through that zone of contamination to clean it up. So that's called a sweep. So push pull on the left and sweep on the right. So I'm going to try to show a couple of quick animations here of how this typically works. This is something called a 5-spot pattern, where you may go into a site because you got a plume that's there and you want to contain and control it. So you establish a recovery well. You can think of this just like one square on a chessboard, for example. So you establish hydraulic control, and then you may have 2, 3, 4, 6 wells around that. I just involve the project in Louisiana like this, where you establish hydraulic control in the center and you're injecting into the outer wells. What's really neat here is when they're injecting the outer wells and the edges of the plume, they're injecting across that band of contamination that was determined during investigation. And what they're injecting of IvySol is pulled hydraulically through that zone of contamination, where it's making that globule, Zorb phase, and NAPL miscible, where it's realized at the central extraction well. And time-based water samples confirm it. Another example of what we get involved with is that sweep I talked about. And that's where you have maybe in this center area here, maybe again, it could be a pipeline, a roadway, a building, I don't know. It could be a lot of factors on sites. So on one side, we establish some injection wells to introduce the IvySol. And on the other side, or in the midst of the plume, we establish some recovery wells to contain and control it, but also to hydraulically influence what we're injecting on one side of the plume through that plume to, again, make contact. And as we make contact, whatever we're desorbing and making miscible will be realized at this one or more recovery wells on the other side. So it gives you some flexibility on how you can actually do the applications. And I'll try to show one more animation during the case study that I'll be presenting today. But the good part about this is over a series of applications, it doesn't take very long to sequentially remove this mass and bring you to a better place. And quite often, if you're dealing with sites where you have floating NAPL or measurable DNAPL, and someone comes along and says use ISCO or ISCAR, I recommend to you to put on the brakes and think twice about this vendor's recommendation. I very seldom have ever seen an ISCO or an ISCAR site with a lot of free phase work without multiple applications. So look at the ticket price of the first application, you're probably doing more. So what we often will do with those clients is we'll go in and remove that LNAPL or DNAPL, then they'll employ that as a separated action, and then they realize a better result. Again, that combination of remediation methods is great. I'm a big fan of it. So now this brings me to a case study that we were involved with near Melbourne, Australia. It was a manufactured gas plant type site. And I'm going to share about this story. We collaborated with a company called Blue Sphere, who was the environmental consultant, and Pacific was the environmental contractor. And something they do differently in Australia compared to here is they actually assign an auditor. They're another environmental consultant with special credentials, where they actually sit on the project as well. So they're kind of like between the environmental consultant and contractor and the regulator, but there's a lot of stakeholder involvement. So you don't get to make decisions in a vacuum. There's a lot of input going on, and I think it's really beneficial. So let's keep moving on. And it's a bit of an abbreviated version, so if somebody looks at it expanded, it's probably in the public domain. Actually, I know it is, but anyways, let me share these slides. So again, here we are. We have a rural gasworks or manufactured gas plant, which is in operation for almost 100 years. A lot of these sites used to be outer fringe of our residential areas. And then as we've expanded our cities and grown, we kind of outgrow these and they become tangled up in agricultural and residential lands. But you can see the various buildings, the retort building, where they basically were distilling off everything. You see their coal pile that's there for heating and all that kind of stuff. You see the gas holders for the gas stuff they would do. They also create some liquids as well. And quite often what they did in these sites back in the day was when they generated any waste, they typically disposed of it on site, sometimes in wells or open pits, unfortunately. But again, like as I said, they're really close to some agricultural and residential areas, which will become apparent in some upcoming images. Yeah. Oh, another thing too is they also produced waste coke debris, hydrogen cyanide, which they call Prussian blue. And if you've ever seen this blue, is absolutely gorgeous, highly contaminated, but it's beautiful color, and some spent iron oxide filing waste. So there's a number of things that occur at these sites, not just the typical contaminants of concern. Yeah, and then they had impacts to soil and groundwater. They did do some gross soil impact remediation back in the late 1990s, but again, it proved ineffective. So there was a lingering issue of liability at this site. So here's a nice image of the site, and in the center we see a couple main plumes, and then they've expanded this off to the bottom left and the bottom right of the image. And so you have here is 2 source zones. What's really interesting in this photo from an air photo perspective is that we got the encroachment of all this residential land and agricultural land where this former gasworks site was located. Interesting, eh? And there's 2 sources again. There's the tar liquor disposal wells. There we go, typical thing. And quite often they had little landfills and or just disposal pits at sites. What's interesting here is that where they had naphthalene, it was a really good indicator of where the NAPL, whether L-NAPL, D-NAPL, and these in-between phase compounds were, which is really good. Let me just keep going here. This is just a legend of some of the things that you're seeing here, but these are the 2 main plumes that they wanted to work on, okay? And the naphthalene at about 100 micrograms per liter had a good correlation with observed TARI type impacts at the site. So just a little bit more information. And one thing I want to say to you is in this bottom left here, you see this little hole, or I'm going to call it a donut occurred. That's where we actually did some bench scale work for this client. Then we went to pilot, then we went to full. That little donut you're seeing is where we actually went in and did some pilot work with Ivy salt and actually removed some contamination. That's why you're seeing kind of a blank space for a NAPL, because that showed effective. We learned from that as to what we're going to do for full scale. So a stepwise process. As our mothers would say, you know, haste makes waste, so walk before you run. I'm a big fan of that, and obviously this was effective in this situation. The objective of the site obviously was to get rid of that NAPL because it was obviously the biggest source of contamination because of you know, diffusion and whatnot through the geology and groundwater, and then, you know, look at the nearby receptors, right? So they wanted to remove those contaminants of concern listed. And associated liability. They also wanted to redevelop the site afterwards, look at the encroachment of agricultural and residential lands. That was a big factor. And obviously, overall, just reduce all the risks associated with the impacts at this site. Now, what's really good about this site was, if you think of that medical perspective, they did lots of testing. They had over 100 wells at the site. So they had a really good conceptual model of this site, which was great. Understood the geology, where the depth of groundwater was. Anyways, from that, we were able to do the applications, watch the patient, keep a close eye on things. We spoke every single week while they were doing this, if not every week, darn close to it, I got to tell you. Anyways, so we were able to tweak and modify things over the process to ensure we had the best results we could possibly have, right? And those 2 main plumes you saw were obviously where we were focusing our main efforts to try to improve them because they pose the greatest bit of risk. I talked to you earlier about how Ivy Sol works without having to form that micelle. So we would inject our products, make contact with the L-NAPL, D-NAPL, and those in-between phases, make those miscible, whereby their multi-phase extraction system, which you were using at the site, would easily remove it. When they were operating that initial oil water, the multi-phase extraction system, yes, they did get some contamination dissolved in free phase, but the rate of recovery became very asymptotic, so they needed to do something to improve it, but it did contain and control things. This just shows them getting set up at the site. In some of those areas that I showed from the air photo, and they were doing a lot of injections like push, pull, and sweep applications at this site. So yeah, they had a couple nice areas to work. The good thing about what we were doing was there wasn't a lot of traffic and we didn't create a lot of noise, so we didn't have any issues with the neighbors, but they made a point of having good stakeholder communications with the local community so that they were aware of what's going on. They've been doing remediation for years, but they realized that stakeholder communication is important to keep everybody content and happy, and they've done that. What I show here is one more animation where they're doing the push-pull. So again, they characterized the site, they knew where the impacts were. We use a lot of existing infrastructure, so we could inject in those wells at certain depths. They could even use a packer if they wanted to control the depth at which it would go in. So they would do their injections at the site, and typically at most of the wells, it was about 1 IBC, which is 1,000 liters. And typically at 2% to 4%, often 2% was enough, so 1 to 50 dilution. They would inject. They could even cause some mounding by gravity feed. You can use low pressure if you need, and again, packers. Put that in where it starts to work on that zorb phase, globules, and then apple phase, and make that miscible, so then they could extract from the same well. As I showed in the previous animations, they could also perform sweeps if they needed to between wells. So it gives you an idea of what they can do, and is an effort to try to clean up these sites. So they were employing push, pull, and sweep applications. This is a nice graph that they prepared of what they were getting for daily and weekly mass recovery at the site. And I'll have to show you some visuals here in a moment of what they actually saw. And as you can see that they were getting a lot of mass over time. And look at this timeline, it's only 120 days. What I will tell you is we cleaned up one area, then we started to double down or triple down our efforts in remaining areas to get that out. And we also learned that when we're dealing with some of the more denapoli type compounds, instead of injecting today and extracting within 24 hours, we started to inject in the morning and pull in the afternoon, we got the most mass out. So we started to pay attention to the patient and how it responded. This is a nice baler that I showed you with all those 3 phases in it. And then over time, we started to see that the balers had less and less product in it. There's from a couple different areas on the site. And there's even a bottle later on just showing a globule showing up at the well. So yeah, you get both quantitative as well as visual evidence. So concluding slide on this, they found that the surfactant-enhanced remediation is a very effective method for cleaning up the site. We had low impact on the local community, and it was a very effective, particularly a cost-effective method compared to other alternatives that they looked at for this site. They liked that the surfactant was biodegradable, free of impurities. We've been tested for, you would not want to know how many things. So that made the regulators quite content. Huge time and cost savings compared to alternatives that they were looking at. And working with the auditor, the site actually went into closure in late 2020, and it's going through regulatory closure as we speak. It's just a slow process given all the COVID issues that they're having down there. And one last image I'm going to show you, there's an industrial site we're involved with 3 layers of DNAPL contamination before and after the involvement of Ivysol, with their objective being to conclude the site by biological means. And all I'm going to say is if you're ever looking at a site with us, we have a 1-page site evaluation form to fill out. From that, we can figure out an in situ or an ex situ strategy for your site, and that could be ex situ bioremediation, for example, soil washing. We determine what our best product is, what the best dosage is, and we provide a proposal to you, and we support that process along the way. As I said, our products are free of unwanted impurities, and if you have any further questions, feel free to contact me, and there's my information. And I thank Joe for having me on board, and if there's any questions, I'll take them now.
Thanks, Bud. Really appreciate that. Lots of information as always. If anyone has any questions for Bud, please type them in the questions or chat. Give it a minute, and we'll move on from there. Bud's contact info is on the screen as well.
Yeah, one of the questions I often get asked, Joe, is will the application and use of Ivysol negatively impact oil water separators and water treatment systems? And again, because we don't cause emulsification, oil water separators still work, and whether you use an activated carbon, MySlex, what have you, they're still effective, and we've never had discharge exceedance in more than 25 years of applying this globally.
Good to know. I see no questions, Bud. So with that, thank you again. And we'll move on to our next presenter.
Thanks for having me. Have a nice day. Bye now.
Bye. Our next presenter is Sylvain Bourdonnais from Trace Associates and Carl Breste from Intrinsic. Sylvain, I think I've shared the link with you to bring up your presentation.
Yes, you have. Thank you, Joe.
And Sylvain's going to be speaking to us on risk-based approach supporting the redevelopment of an urban lead impacted site. So I'll turn it over to you.
Thank you, Joe. Can you see my screen?
Yes.
Okay. So good morning, everyone. My name is Sylvain Bourdonnais. I'm Principal Risk Assessor at Trace Associates, and this work was done in collaboration with Carl Brese at Intrinsic Corporation. And the topic of the presentation today is a risk-based approach that was used to support the redevelopment of an urban lead-impacted site. So an outline of the presentation today. I'll give you an overview of the site background and the history of the site, then the management goal for the site, a bit of remediation that we did, and then the bulk of the presentation will be on the risk assessment for metal exceedances. So both aspects, lead, human, soil direct contact, and a few slides on the metal ecological soil direct contact, conclusion for the slide, and a project sustainability summary. So let's jump in. The site background, what we're talking about is a vacant land in an urban setting. The land is subject to residential development with a proposed retention pond in the middle. Historically, the site had a ravine going northwest to southeast. The ravine was filled with suspected historical dumping of debris from the flour mill demolition. And what we found on site are inert debris, so bricks, metals, clothes, concrete, whatever you can find in the building, in the initial building. And to illustrate this, a few historical photos. So you can see on the left from 1994, we can see that the ravine is going from northwest to southeast on the site. In 1971, we can see some dirt work and happening at site. And obviously in 2002, the slide is totally flat. We can still see the ravine coming from the north, then it disappears and kind of reappear in the southeast. So the site management activities that were done in between 2015 and 2019, Trace did some soil and debris characterization and also some excavation of the larger debris. 2019, there was a formal soil characterization program going down to a maximum depth of 9 meters below ground surface, 22 boreholes that you have on the figure, and 2 test pits, so all across the area of the former ravine. What came out of this soil characterization are exceedances of the Tier 1 guidelines for hydrocarbons fraction 3 and 4, metals and PAHs, and an estimated volume of 23,000 cubic meters of soil with exceedances. From there, Intrinsic did the preliminary risk assessment. So here you have the result of the risk assessment summarized on the table with different group of COPCs and the different exposure pathways that were considered for the site. We can see that for metals, the metal exceedances were related to the human soil direct contact and the soil ecological direct contact. For PAHs and PHC, we've got exceedances of the domestic use aquifer and freshwater aquatic life for PAHs, and human soil direct contact, ecological direct contact, and management limits for the hydrocarbons. The risk driver at the site, all the exceedances for PAHs and PHC were fairly localized, and you'll see in the following slides, but the risk driver for the site was definitely the lead impact and the exceedances of the human soil direct contact guidelines. The management goal for the sites, the remediation to Tier 1 guideline was considered overly conservative for the site because, again, we're going to have, so we have a very large volume going very deep. The site is going to be redeveloped with a stormwater pond in the area of the former ravine, so there will be limited soil contact. However, the risk management plan was not the preferred approach. So just considering that we're going to have a barrier in the soil and was not enough, especially for there was some concern for the associated future liability. So the plan was to develop site-specific remediation objectives for the site based on a site-specific risk assessment. So this falls under a Tier 2 SSRA approach. Then going back to site, remediate the soil to the site-specific remediation objectives, leave in place and or reuse the soil that was below the sites, the SSROs, but still reusing the inert debris as reclamation material. So how did we do that? Let's first look at PHEs and PHC exceedances. Pretty straightforward for those two. They were localized on site. The PHC exceedances, because they were above the management limit and they were limited to few locations, we decided to excavate to 2 test pits that were completed in spring 2021. We still have the localized PAH exceedances that are associated with some asphalt debris in the ground, so most likely non-mobile. Those localized PAH exceedances will most likely be excavated during ground disturbance works at the site. Now we left with the biggest issue, the metal exceedances, to concern the human and ecological soil direct contact exceedances for lead, and some ecological soil direct contact for other metals. All those exceedances are basically spread across the site, as you can see here on the figure. Everywhere where the ravine was backfilled as exceedances for metals. Main concern are the exceedances of the Tier 1 human direct contact guidelines for lead. That's the risk driver. We also have exceedances of the ecological direct contact guidelines to consider, especially for arsenic, chromium, copper, lead, nickel, tin, and zinc. A bit on the data distribution, so how big is this issue? 38% of the sample had exceedances of the human direct contact guidelines for lead. And there was a lower frequency of ecological direct contact exceedances, so less than 5% for most of the metals, except for lead and zinc. So 70% of the samples were exceeding for lead and 30% for zinc. And this is illustrated with the lead, with a graph here on the side, where you can see the soil lead concentration and the cumulative percentile of the data distribution. And so we can see that approximately 62% of the samples are below the lead human guideline. So again, we are left with 38% above. And for the eco contact, it's 83% below the guideline and 17% above the guideline. Maximum concentration of 2,400 milligrams per kilograms with a 95th percentile of 580. One thing we did for the metal exceedances, for the metal impact, is since we had to go back to site to do remediation of the hotspot of the exceedances for PHC, we also did some remediation for the hotspots for lead. So we basically targeted all the locations where lead was above 500 milligrams per kilograms. So this is illustrated on the graph on the side. So the blue line is before, is the one that I just presented, which is before the hotspot remediation. And the orange one is a new data distribution. We still have 35% of the sample above the human direct contact guideline and 14% above the ecological direct contact guideline. So the approach to deal with that is to do a site-specific risk assessment and see what we can do. First aspect of the risk assessment was a human health risk assessment for the soil direct contact for lead. Some information about the toxicity of lead. It reduced the cognitive development and intellectual performance, especially in infants and children, which are the most susceptible subpopulation. The guideline from AEP was adopted from CCME 1999. It's a pretty old guideline. It's based on a tolerable daily intake of 0.00357 milligrams per kilograms per day. And it also considers health effect as threshold effect. The guideline was calculated based on a lead bioaccessibility of 100%. So knowing that the bioaccessibility of lead can be highly variable in soil, what we decided to do was to estimate the site-specific bioaccessibility, or calculate it, and then recalculate the guideline based on that. So we went back to site, collected some soil samples, and we did some in vitro bioaccessibility test on those soil samples. So those soil samples were selected to represent a range of lead concentration representative of the site, so both maximum and lowest concentration. The bioaccessibility test is an approved testing protocol by Health Canada and US EPA. It basically considers the dissolution of soil in a stomach, so it's done through an acid extraction, and it excludes the adsorption rate in the small intestine. However, there is an established empirically relationship between the in vitro result and some in vivo test. So you can use an equation to calculate your result from the test. So considering just the dissolution in the acid extraction, and then bring it back to a more representative in vivo bioaccessibility. So we did those tests, and the result came back with a bioaccessibility of lead of 77%. From there, we used this value and we did recalculate the lead human soil direct contact guideline. We also changed the dermal absorption to use a recent one that was published by Wilson and Richardson in 2013. And we use the equation that is provided by Alberta for threshold substances. The initial guideline was 140 milligrams per kilograms. The new site-specific guideline is 171 milligrams per kilograms. So what do we get with that? It's better, but we're not there yet. So this is a lead distribution compared to the new site-specific guideline. So you can see on these box plots that we still have some samples that are above the guideline, which actually represent 29% of the samples. So what can we do? What can we do from here? And how much remediation do we need to do to reach an acceptable level of risk? So we used an exposure assessment approach, considered 4 remediation scenarios that you have here on the table. So no further remediation, remediating to 400 milligrams per kilograms of lead, 350 or 300 milligrams per kilograms. We used the 95% upper confidence limit of the mean as an exposure point concentration. So because we're dealing with humans that are mobile receptor, we can assume that they're not going to stay at the most impacted area all the time. And so this 95 upper confidence limit of the mean is more representative of the exposure of humans. So we did calculate the different 95 UCLM based on remediation to 400, 350, or 300. And it gives us exposure point concentration ranging from 130 to 198 milligrams per kilograms. And this is based on more than 59 sampling points. So if you look at on the box plots again with the 4 different scenarios, we can see that basically between 350 and 400 milligrams per kilograms, using this value as a remediation objective, that's when your 95 upper confidence limit would go below the guideline. So based on that, a site-specific remediation objective of 350 milligrams per kilograms was considered acceptable and leading to an acceptable level of lead that does not present a risk of adverse effects to humans. One other thing to consider in this is that all of this approach does not account for the exposure barrier that you would have between the soil and the human receptor, because again, we would have this stormwater retention pond and some kind of a park around with some new fill on top of the contaminated soil. So now that we've dealt with the human soil direct contact aspect of the work, we are still left with some exceedances of the ecological soil direct contact to deal with. So again, arsenic, chromium, copper, lead, nickel, tin, and zinc. So when we did a risk assessment, we did an exposure assessment using the 95th percentile of the data distribution. We didn't use the 95 upper confidence limit of the mean because in this case, it's ecological receptor, plants and invertebrate. So we consider them as non-mobile compared to humans. And so, but the maximum concentration seems overly conservative. So we decided to go with the 90th percentile. And what you can see on this table is if you compare your 90th percentile to the ecological guideline, all of them are below the guideline except for lead and zinc. So we looked at the guidelines for ecological direct contact and how were they developed, especially the toxicity data. So the toxicity data is based on sensitive species, so fairly conservative, mostly some agricultural plants that we will most likely not find them in the area of the pond. Some sensitive endpoints, reproduction and growth, and conservative benchmark values, especially so the no adverse effects, some no adverse effects level. So based on that, we looked at the data distribution, so the current one, and what's going to happen after we do remediation to the site-specific remediation objective for the human direct contact. So here on the left, you've got the box plots for lead concentration. So the dark blue is the current one, and the light blue is the expected data distribution after remediation to the SSROs. So we can see that we can expect the 90th percentile, which is a star, would be below the residential ecological direct contact guideline for lead. For zinc, it's a slightly different story. In the current condition, the 90th percentile is 394 milligrams per kilograms. It is above the residential ecological direct contact guideline. If we do when we're going to do the remediation for lead, we'll also remove some of the zinc impacted soil that is associated with the lead impacted soil. So that would reduce our 90th percentile for the zinc distribution to 306 milligrams per kilograms. This is still slightly higher than the residential guideline. However, we are way below the commercial guideline. And the difference between those two guidelines is the residential guideline is based on the 95th percentile of the distribution for sensitivity species distribution. So it protects 75% of the species. The commercial guideline will protect 50% of the species less protected, likely enough for the future land use. So based on this, we're not expecting any severe adverse effect on plants and invertebrate populations if we do the remediation to the SSROs for 350 milligrams per kilograms for lead. In conclusion, so the risk assessment was associated with partial remediation, so for PHCs and the lead hotspots and some PAHs in the future. We developed site-specific remediation objectives for the lead based on site-specific guideline for human soil direct contact. So that will allow us to do more remediation. There is no severe adverse effect expected on plant and invertebrate population after remediation to the SSROs. And then two things that I want to highlight on this project is first, the importance of communication with the regulator and with the stakeholders during the process. And then I have another slide to show the safety, environmental, and financial benefits of this SSRA approach. So again, initially we were estimating a volume of soil to be excavated and removed from site of 23,000 cubic meters using tier 1. This has been reduced to a very conservative number that we've calculated of 8,000 cubic meters. So we have a saving of 15,000 cubic meters of soil that will not go to a landfill. And so associated to that, you have 72,000 kilometers of travel that are avoided. Even if this is an urban site and the landfill is pretty close, the total remediation, like the 15,000 cubic meter saving, is associated with 72,000 kilometers. 67,000 liters of fuel, all the associated greenhouse gas emissions that would be avoided. This is equivalent to 1,890 trees planted. You obviously reduce the nuisance in this area during all the remediation work and the damage to the road and all the safety hazards. And there is obviously a cost saving that was estimated at $5,500,000. Just a thank you to the Environmental Sciences Group at the Royal Military College for the bioavailability testing. A few references, and if you have any questions, we're here to help. So you can contact either myself or Carl at Intrinsic, and I will welcome any questions.
Thanks, Sylvain. Carl's on the line as well. Carl, did you want to add anything? Or was there any questions for either of them? I don't see any questions at this time for you. So thank you again for presenting. We'll move along to our next presenter.
Thank you very much.
Thank you, Joe. Thanks, Sylvain. Good job.
Our next presenter is Matthew Beveridge with Hemera.
Hello, everyone.
Hello, Matthew. You should be able to share your screen now. Matthew's going to be speaking to us today about in situ remediation of dissolved metal plumes from concept to full-scale remediation.
I'm not sure.
We got all your emails. Oh, family photo.
There we go. See that now?
Yeah.
All right, let's hope it goes to the right one. All right, all good?
You just need to click the display settings a second at the top.
The second at the top.
It says show taskbar, display settings.
Show taskbar. All right.
Next one. Nope, next one.
Oh, display settings. Yep.
Yep. And then swap presenter view, and you're good to go.
All right. All right. Well, so everyone can hear me then, and you can see my screen. I'm taking it.
Yep. Everything's great. Thank you.
Excellent. Thank you so much, Joe. Well, depending on where you are and you're watching this, either good morning or good afternoon, and thanks for attending this discussion. I'm going to talk about a project that I've been managing now for a few years here in the city of Calgary, where I'm based, and this is going to be the in situ remediation of a dissolved metals plume. And I'm going to go through that project from concept, pilot, up to full-scale remediation. So as I get going, what we do in Hemera always when we have meetings, we always have a values moment. Could be safety, could be just a shout out to someone. And for this project, I think something that's really applicable is just being one of our values, open, honest, and collaborative. This project has really been a collaborative approach from the start. We've engaged with different groups, different subcontractors, different consultants, regulators, as well as stakeholders on the project, just to come up with a solution that will work for everyone. We've had those open and honest conversations, and they haven't always been easy, but they've really helped to push this project forward. And we continue to have those conversations with the key parties just to make sure that they understand where we're going and where things are falling with results. And so, you know, for everybody that's on this call today, I'm welcome to have a conversation afterwards. If you want to have questions or anything, of course, I'll leave a few minutes for that. But feel free to reach out afterwards. I'm always keen to hear feedback and how we could potentially collaborate on projects together in the future. So just a quick introduction and outline on what I'm going to speak to today. Just a quick project introduction, a little bit of background on the project site, some of the challenges that we came up across in this project, and there were a lot of them. Then we'll get into what we called phase one, which was the bench scale. And we kind of broke this out into 3 phases to make it an iterative approach where we could continue to develop the project based on the most recent information that we found. And I find that on projects that really allows you to develop and continue working towards your end goal or objective, and to get a better objective. And, you know, there's cost savings, there's time savings on that sometimes towards the end of it. So phase 2 of this was then where we went out to the field and we actually did pilot scale testing of our remedial approach. And phase 3 then was the full scale. We're currently right now in a post-injection verification phase. We're about a year out from when we completed our last injections for the in situ remediation. So we're still collecting data and assessing that. And then at the end, I'm just going to go on to some lessons learned and important things that maybe you can take forward into some of your projects, into some of your clients as well. So just to get into it, project introduction and some challenges that we had. This site that we're working on was a former industrial and it's currently a commercial site. And that poses its own challenges with it being commercial. And today is Thanksgiving in the US and it's Black Friday tomorrow. It is a very busy commercial site. We had to work at night. We had limited access to areas with all the developments that are on it. So that really, you know, put a challenge on our team and our constraints on when we could work, how we could work, and how we needed to develop this remedial design. The source zone of the copper plume was also inaccessible. It's underneath a major intersection right within this commercial development. We weren't going to go out and dig up this source zone. There's utilities, there's stoplights, you know, we just couldn't get at it. So we needed to come up with an approach that would sequester and keep that source zone, you know, from continuing to discharge copper at concentrations greater than the Alberta Tier 1 guidelines. So that was another challenge that we needed to address. And one of the things that we did find is that we did some modeling through Freaksy at the start of this to kind of develop our conceptual site model and how we anticipated that copper to continue releasing into the environment and into the groundwater. And we showed that, you know, up to 700 years, that this plume was going to continue to discharge copper into groundwater, which then goes into a freshwater aquatic receiving environment, and that those copper concentrations would continue to increase. So we're currently already above the tier 1 guideline of 0.07 milligrams per liter. And so we're looking to go up to about 0.3 milligrams per liter in the future. So that's a major concern in trying to protect this in freshwater aquatic receiving environment. And one of the last challenges we had is just the aquifer conditions. This is a very, very fast flowing aquifer. We have movement of up to 1.2 meters per day in that groundwater, and so it's tough to control the injections and to keep our injected materials within the area that we want to keep them to precipitate and form our remedial option. So we needed to work with that. And then, as I mentioned earlier, just limits on working on site due to the commercial nature of the property. So just some of the sequencing that we went through. Again, I mentioned earlier, we kind of went through a phased iterative approach, taking our lessons learned from each groundwater sample, each injection, and taking that to the next day and trying to make it a better program. So we started off with the development of our conceptual site model and then our remedial options evaluation. And this kind of set the stage for what we thought would work given our constraints and our limitations. And then we kind of took that to the client and to the regulator and said, is this something that'll work for you on these timelines and these costs, of course, for the client, and then for the regulator on timelines and, you know, feasibility of if this can be acceptable, because it hadn't been done in the province of Alberta previously. In 2018, then we went into phase 1, which is where we started doing additional investigations. So, you know, areas that we didn't have delineation on the plume, we drilled to get that. We also took site groundwater and site soil and started doing some bench scale testing. And each of these phases, I'll kind of get into more details as I continue this talk. Phase 2 in 2019 was the pilot scale. So we went out to site, and this photo of one of my colleagues out on site is when we started doing the injections. Obviously safety being a major concern when you're handling different chemicals for injecting. Phase 3 in 2020, so last year, we did the full scale remediation where we were working with a subcontracting partner to inject various chemicals into the ground as part of our remedial option or remedial strategy. And then ongoing right now, like I said, we're still in post-remediation verification. So we're following up with additional data collection, looking at the efficacy of this remedial approach that we took, and in discussions with AEP and our client to inform them of how things are going. So just stepping back into the conceptual site model, if you look on the left of this figure is kind of what we have visualized for the site. It's a fluvial aquifer, fast flowing cobble and gravels. We have underlying that a bedrock, which is a little bit fractured at the top, but mostly competent. So we don't have any, we have vertical delineation. It's not going into the bedrock. Above our copper zone, as I mentioned, is a former industrial site, now commercial, with a major intersection, so we can't access it at any point in time. Groundwater flow coming through that source is taking this copper, putting it into the dissolve phase in groundwater, and flowing towards this freshwater aquatic receiving environment where copper is toxic to marine or to life in that river. So our conceptual model for the remedial approach was to develop hydroferric oxide in the aquifer, and the approach that we took to do that is to precipitate this material out through injection of ferrous iron and then an oxidant. And the intent for removal of the copper from groundwater is by two approaches, one being copper being absorbed onto that HFO surface, and the second being removal via co-precipitation as the HFO is forming. So that's kind of what we worked with and the data pointed to, and in discussions with other subcontractors and colleagues, this was something that we felt we could deliver appropriately given the constraints that we had, and that it would have an effect, but we needed to move forward with a little bit more information first. So the remedial options I mentioned is this injection and sequestration via HFO. Some of our background studies showed that HFO in lab settings can remove copper as well as other metals. Some concerns that we have with this though is that as you're generating HFO, this reaction of ferrous iron with an oxidant, it is acid generating. So we needed to confirm that by injecting these materials and generating HFO, we wouldn't be lowering the pH and thereby releasing more metals. So some of the baseline studies in that conceptual site model were to test the abundance of calcite, which could buffer that potentially. So we did some assessments and found that yes, calcite was present at an appropriate number that we could buffer that pH out. And then looking at the options again, constraints, limitations, we felt this was a cost-effective method where we could drill injection wells, around the copper source, down gradient of the copper source, so that we could work within the limitations that we had of inaccessible copper source and not being able to work all the time out on the site given its nature. And with that, we were able to select our reaction materials, select how fast we wanted to inject, and kind of develop that all, which really worked towards, being able to get on site, effectively deliver these materials to create that reaction and then precipitate out the HFO. So going into phase 1 back in 2018, we wanted to increase HFO in the aquifer solids, and to do this, we were looking to use injected site groundwater and have a 1-day residence time. So we did some column testing, and so within that column we used 3 columns that we amended with HFO, and then we had a control column, and within that column we used site aquifer materials, and then we took site groundwater and we pushed it through those columns and collected at various ports along that column for dissolved copper concentration. So some of the results that we found is the influent was about 0.3 milligram per liter, and tier 1 in Alberta is 0.007 milligram per liter. And the graph on the left, the column A, is where we injected 5,000 milligram per kilogram of HFO. Column 4, which was our control, we didn't add any HFO. You can see the red line being the influent copper concentration, and then that kind of dark teal line being the effluent copper concentration in the groundwater. And we found that HFO in these column tests for the 3 concentrations of HFO that we used were very effective at bringing that copper concentration down below the tier 1 guideline. Whereas when unamended, there was a little bit of removal of the copper. We attributed that to there is HFO already present in the aquifer materials, as well as some organic matter that would remove copper as it flowed through. So coming out of the bench scale testing, we felt that the baseline aquifer that we tested was about 500 milligrams per kilogram. It can remove some copper, but not enough to get it down to that tier 1. So we did test the 3 concentrations, 3750, 5000, and then 6250 milligram per kilogram. And for all of those results, we show we got below the tier 1 guideline, which is the desired outcome. We followed that up with the sequential extraction testing of the aquifer solids in the 3 columns that we used. This was called the BCR test. Another method that you could use, if you've heard, is the Tessier analysis. So what we wanted to do there is just to see if once that copper is absorbed onto the surface of the HFO, what's going to happen to it long term? Will it release in the future, or is it going to be a stable, particle there? So we did find that HFO that is generated by the reaction we were going to use is not water soluble. So we didn't anticipate that it would be released in the future. And so that copper would be sequestered on those surfaces long term once we had amended the aquifer with the HFO. So coming out of this, we felt HFO was an effective mechanism for the sequestration of copper in the site soil and groundwater. And from there, we went into 2019, where we moved into phase 2 of the project, which was the pilot scale injection. So the figure that I have here, and I'll just explain a little bit, is we wanted to go out and test similar to the pilot study with those 3 concentrations of injected HFO to see which one was the most effective. Could we be on the lower end of the injected materials, or did it need to be the higher end? And of course, this will be a cost savings or an additional cost for the client to do this. And so we tested it on 3 transects. And if you're looking at the figure, you'll see there's kind of yellow arrows pointing down towards the bottom right. These are the 3 transects where we injected in the top with groundwater flow moving towards the bottom of the figure. So we injected in the IW wells, and then down gradient, we had nested wells labeled 11AB, 12AB, 13AB. And then further down gradient, again, about another 10 meters, was another well to monitor the injection and then the groundwater quality afterwards. So we did this and we injected the amendments to precipitate the HFO. So we used a ferrous sulfate, and then we used calcium peroxide. Those were our initial test products to see how we could do this on our own. And the rationale for choosing those is ferrous sulfate, safe. Calcium peroxide, it was a solid, we mixed it in water. So again, safe to handle for our field crews out there. And we did this in a batch style injection. So we took a cube of water, mixed in ferrous sulfate, just used hydrostatic pressure to flow into the groundwater wells, and then followed that up with the calcium peroxide as the oxidant. And then again, monitored those down gradient injection wells to confirm, were we getting ferrous iron in groundwater? Were we seeing DO increases, changes in the oxidation reduction potential, and how that reaction was progressing? So some of the things that we did as we were out there, and here's a photo you can kind of see, is again, alternating the amendment injections. We looked for mixing in the aquifer and the HFO precipitation. And some of the lessons learned that we took from this is that, initially we had thought groundwater flow was towards the southeast, but the size of the site, overall groundwater flow was to the southeast, but in our pilot scale area, groundwater flow actually was more on a southerly direction. So it did vary from what we had anticipated. We also determined that the target dosage was going to be effective on the lower end, so that 3750 milligram per kilogram. And from our challenges of using the calcium peroxide and getting it into the water in these totes, it was insoluble, so we decided that we needed to go with an oxidant change, something that was a little easier to get into the water, something that was a little bit more reactive in releasing oxygen for that oxidation. And we also figured that the batch style wasn't going to work. Again, given the limitations and constraints on the site, we needed to get in, inject as much as we could, and then get out so that the commercial properties could operate as they were. And the batch style, by having things on site, blocking off parking, the tenants and the client weren't happy with that. So we decided to rethink our injection method and kind of go with something that was more continuous. And so we needed to change the design of it. And that kind of went into our next phase. But the results that we found from the pilot were in line with what we saw on the bench scale testing. And so the two figures you're going to see here on your screen, the one on the left, the chart, the orange line is the dissolved copper concentration. The blue line is our dissolved oxygen concentration associated with that sample. And what we found is that where the dissolved oxygen was the highest, our dissolved copper also was decreased and got below the tier 1 guideline. And so from that, we felt where we saw dissolved oxygen increase meant that we had the full reaction, the generation of the HFO, and then the sequestration of the copper. Whereas on the periphery of the plume, so the east or west side of it, we didn't have that because it wasn't directly downgrading of the injection. And again, the figure on the right is just showing that groundwater flow wasn't southeast, it was actually more to the south. And down gradient in these dark blue is over 90% reduction in dissolved copper from baseline. So the periphery on the left or the right where you see the red and orange, there was some removal of copper, but I think that was more just kind of as groundwater flows, there is some radial flow from the injections that caused that. So down gradient, we had good removal, and that gave us faith that we could move forward into full scale in 2020. This is just one of the setups that we had working with one of our partners on this, Trium Environmental. So we designed this with 3 injection areas to manage the source zone and then to manage groundwater that was down gradient of that source zone. So source zone, again, inaccessible. Transect A was about 150, 200 meters down gradient of the source zone, and we designed this to be perpendicular to groundwater flow so that we could, cut off or treat as much water as possible. And then Transect C was about 20 meters up gradient of the freshwater aquatic receiving environment where this groundwater plume discharge. And again, it was kind of that last scrubbing, buffering of the groundwater prior to discharge. And again, the idea behind it was to try and stabilize the source zone, minimize further down gradient migration of copper by the Transect A and Transect C, and then, effectively to protect that freshwater aquatic receiving environment. So some of the things that we did, and I mentioned earlier, we used calcium peroxide to start. We ended up changing that to a hydrogen peroxide Having it as a liquid was a lot easier. Working with Trium, we were able to blend it down, and it was a safe, effective mechanism for delivery. And in the design of this permeable reactive barrier, we did some tracer testing where we used table salt, and we just monitored down gradient of wells while we injected into one well and extracted out of another. And we were trying to create a stagnation zone between that injection and extraction well so that we could react and precipitate out that HFO within a small area. And we felt that that would be the best approach for delivery of the HFO and for the remediation. And so we also changed from a batch into an injection kind of recirculation. So the end design that we came up with, and you'll see the figure on the right, is what we called 6-pack. So groundwater flow on this figure is towards kind of the bottom right-hand corner of that figure. And so the 6-pack here in the injection methodology was we have 3 wells on the up gradient side. We put extraction pumps within those 3 wells. The 3 wells on the down gradient side of the 6-pack is where we injected. And again, by trying to recirculate against the natural groundwater flow, we wanted to make that stagnation zone. And then down gradient, we had a well at about the 5-meter point in the center of that 6-pack for monitoring. And then we had another one at about a 10 meters. So it was about 15 meters from the injection point. And the intent of these wells was just to monitor groundwater quality, the progress of the reaction, and if we needed to shut down because we saw ferrous iron moving further than we wanted it to, we could shut down the injection and just extract and try and pull it back. So that was kind of the design that we went with. One of the things that we did in those down gradient wells was that we had real-time data collection with data sondes, aquatrols, and we also used test strips to ascertain that we were precipitating the HFO. So we had test strips for iron as well as test strips for hydrogen peroxide, just to give us an idea that yes, we were precipitating it out. Yes, we were, seeing hydrogen peroxide come through, but not the iron. And you'll see one of these samples here this is just some of that ferrous iron and some of it being precipitated out kind of as that rust, which is the HFO. We did find that we were able to control the groundwater via this injection methodology. So we did have that stagnation zone created. And we didn't see at some of the 6-packs any iron showing up at the 5-meter down gradient. But again, when we did, we were able to shut down. And having these real-time data collections, we had a dashboard set up where myself or our senior hydrogeologist, as well as the client, could log on at any point in time, take a look at the data being collected and what it looked like. So if we saw a pH drop, I could give a call, or the hydrogeologist give a call. If we saw DO spikes, we knew that things went to completion if we didn't see any iron. So it was really nice, especially with some of the work having to take place at night, that we could take a look the next day and kind of inform the field team of any changes or anything that needed to be made. And end results, what we saw were down gradient of where we got our target mass of copper into the ground. We saw 99% decreased dissolved copper concentrations. And when I say where we got target mass into the ground, we did have some troubles. Some wells just weren't able to take as much of the injected material as possible, and so we'd have to shut down. Either that's due to fouling, or the bentonite seal around hadn't been fully saturated, and so we had kind of bubbling up around the annulus of the boreholes. So we did have to shut down and kind of adjust on the fly, but that's where this real-time data collection, and we had tablets in the field that had kind of warnings and notes to the field team. If you see this, think about taking this step or changing your injection or slowing it down. So it was really quite iterative, even in the field doing that itself. And following up on that, our post-verification modeling that we have is showing that our bench scale and pilot, which showed great decreases in the dissolved copper, is also now showing up after this full-scale remediation, which is really nice to see. And this is just some of the initial data that we've collected over this past year. And you'll see kind of what we've done is we had baseline data back in 2020. Those are the furthest on the left. And then throughout 2021, we've collected 4 samples to date, just to confirm those results. And you'll see, the tier 1, some of the areas we are getting down below it. But the key idea again is just to remove some of that material, the copper, from the source zone as it continues to flow. And so the 2 bottom results, these PR20Cs, are down by the river. trying to get those ones down below the tier 1 is kind of what the end of goal was. So what we did find though is where we injected the iron, if we got our target mass injected into those wells, we had really, a lot better decreases. Where we weren't able to get as much iron into the ground, we saw less decrease dissolved copper afterwards. So again, it's just, you're going to have less HFO generated, less sorptive capacity within that area where you have less of the iron injected. So just some lesson learned that we've come across on this project site, and which I think is probably applicable to a lot of projects that we do in this industry and any industry, is just, understanding your site conditions is really important. As I mentioned, getting good baseline data is really going to help you design and develop that conceptual site model so you can go through your remedial options evaluation, put some options on the table, as well as get some better costs and timelines for your client, as well as for any regulators you need to discuss with. We had some changes and we had to pivot a couple times going back to the pilot in 2019 where we thought groundwater flow was in a southeast, turned out to be more southerly. Had we known that, we probably would have adjusted our kind of transect design and development for that point. But getting into full scale, we took some tracer tests so that we could really design the injection methodology, the design of how the wells would be laid out so that things were completed up front. And it really, was a benefit to the project and that we were able to get it done afterwards and see good results. Another thing too, kind of going back to my values moment at the start, is just to engage with stakeholders at the start and just don't let up on it. We've been in constant conversation with AEP, constant conversation with the tenants at the commercial site so that they know when we're coming out, what we're doing. If they have any concerns, we don't have to go out at that point in time, we can wait. And getting that feedback and getting that information into us allowed us to design a method where, in one night we could get out, inject a target mass of iron or, a percentage of that target mass, and then maybe go back and finish the next day, and we would have no implications or no impacts to the commercial operations. So, getting their input, getting their thoughts was really important to building this program. And then again, I always like to have my programs done iteratively, taking those various steps, building upon them with what you've learned from the previous step, really allowed us to design this program, take it from bench scale all the way now to the post verification. And we're getting great results, I think, because of that iterative process where we were able to learn, change on the fly. And it really helped, give our client as well as the regulator confidence that we weren't just going to go out and dump a bunch of things into the ground and hope for the best. We took a stepwise approach that was going to get us the design and the result that we want. And then just be ready for setbacks. I mean, nothing ever went perfect on this. We're getting good results right now, and I'm really happy with it. Keen to see what it'll look like in a year or two from now. But things do change. And again, if you do it in an iterative process and a phased approach, that allows you to make those changes and to take those setbacks and use them as lessons learned to move forward. So I think the end of this, kind of what I'll say, is that we have found that HFO, or hydroferric oxide, is an effective method for removal of dissolved copper in groundwater. It can also treat other metals, lead, arsenic, cadmium. If you're going to go forward with this type of approach in the injection, reaction, and precipitation of HFO, I think that there's some lessons learned you could take from this. But it can be used either, for remediation or even in the design of a commercial property or an industrial property where you might think that metals or dissolved metals in groundwater are going to be a concern. You could lay down a foundation, or not a foundation, but lay down HFO on the bottom and then build on top of that. Let's say, for example, if you're doing some sort of a mine tailings where you think metals leaching out in the future is going to impact your groundwater. That's something that we've kind of looked at and potentially exploring, but it has worked on this site. You've obviously got to take into account your site conditions and how to design what you're going to be doing, but it has worked from bench scale up to full scale remediation. And I'm happy to report that things are going well and we're getting good results, and hopefully next year we can have a talk and show you a little bit more about it. So thanks everyone for listening today, participating, and if you have any questions or comments, feel free to give me a call, send me an email. Always happy to talk about projects and how we can collaborate together.
Thanks, Matthew. If anyone has any questions, feel free to type them in the box. I'll relay them to Matthew, or you can reach out directly to him. Hey, Matthew, I don't see any questions at this point for you. Some might come up later, but thank you again for presenting today. Really appreciate it.
No problem, Joe. Thanks for pulling this together. It's great to talk with people and see other things coming up.
Yep. Thank you.
All right.
Now, our last presentation of the day. Sorry about the pronunciation of the name, Mede Montevassellin at the University of Manitoba. I shared the link with you. You should be able to bring up your presentation. Speaking to us on bioremediation of chlorate and chromate contaminated groundwater in cold climates. Hello,
Hi.
did you get
Thanks.
the link?
Not yet.
Okay, try again. There we go.
Oh, you have it?
Yep, now just put it in. Yeah, you just need to go into presentation mode, please.
Oh, okay.
There you go, perfect.
Hello, everyone. As Joe said, my presentation is about bioremediation of chlorate and chromate contaminated groundwater, specifically in cold climate. And I did it under supervision of Dr. Beata Gorczyca and Dr. Richard Sparling from U of Manitoba and Indra Kalinovic from Dillon. As you see here, chlorate is one of oxyanions of chlorine, which has wide use of in North America in different forms. It's been produced as sodium chlorate, calcium chlorate, potassium chlorate, and magnesium chlorate. The major use of that is bleaching in paper and pulp mill industry, but there are few places that use as herbicide still. Health concerns about chlorate. We know that this material could be fatal in concentrations 100 milligram per kilogram of body. In lower concentrations, it has a negative effect on blood and thyroid. Canadian regulations regulated this chemical to be lower than 1 milligram per liter in drinking water. We don't have any specific value for recreational water, but it is regulated for drinking water in Canada. For chromate, you can see chromium is a chemical with 6 valence electron that can accept different forms of ion. It has a wide spread of use as chromium trioxide, chromic acid, potassium chromate, and sodium chromate. There are different ways of to use it in making metallic alloys, textile dyes, and paint pigments. About health concern, inhalation of chromate can attack our respiratory tract and kidneys, and our eyes and the skin can be irritated in case of touching that. Regulation says that in United States, the amount of chromium, total chromium, should be lower than 0.1 milligram per liter, and in Canadian guideline, we have half of that value, it should be below that 50 microgram per liter. Chlorine ions stability, you see here, perchlorate and the chlorate are stable forms of chlorine oxyanions. They remain in the environment if we do not do anything with them. For chloride and hypochlorite, we don't have any problem because they are unstable forms and they change to chloride by themselves easily. Perchlorate and chlorate reduction process, it's a long path that happens in preplasma of microorganism. It's an outer layer of cell, and perchlorate or chlorate reduced to chloride and hypochlorite there, and then cells use the oxygen as their source and release chlorine ion to the environment. For chromium, we need to know that the most stable form of that is chromium-3, and chromium-6 is semi-stable. For chromium-3, we can see all the amount of natural occurrence of chromium in the environment is in this form, but chromium-6 can be seen in some areas, but it's not common. Why? Because the reduction process from chromium-6 to chromium-3 is really easy, and in presence of electron donor, even in chemical paths, it can happen. But the oxidation process from chromium-3 to chromium-6 is not favored in nature, and it takes a long time to happen. So the major amount of chromium is in form of chromium-3, and chromium-6 has anthropogenic source. Bioremediation is the method that, despite other methods like chemical remediation, physical or electrochemical remediation, it doesn't have any contaminant at the end, and we don't need to think about further processes for byproducts. It can be done in two ways: in situ or ex situ in the bioreactors. In situ method, it can occur naturally in the environment and we just observe it. Also, what we focus on is engineered bioremediation. It can be done in two ways: biostimulation or bioaugmentation. There are several parameters affect bioremediation process, type of microorganisms we have in the environment, bioavailability of our contaminants, and also other circumstances like osmosis pressure, oxygen content of environment, temperature, pH, and moisture. What caused this project to be done? It was a really common way to dump waste in chemical plants in the past, to have some lagoons and just send the waste there. The water content evaporated there, and the chemicals remained there safely with a safe distance from groundwater. By emerging new technologies, in 1990s, many of these lagoons abandoned, and to safely abandoning them, they are just covered by soil. This soil cover could protect them from many environmental issues. But what happened after decades? the precipitants, precipitation of the weather, rain, snow, and any other thing that could penetrate the soil, dissolve the chemical content of these lagoons and release them in groundwater. In the site that we focused on, that we had the worst case of chloride 3900 milligram per liter, which is much greater than 1 milligram per liter, which is regulated. And the concentration of chromium-3 in some wells reached up to 3 milligram per liter. There are some questions here. Why these chemicals don't reduce by themselves? It might be absence of reducing bacteria. It might be lack of proper chemicals like electron donor or nutrients. The objective of this project is determining the ability of the microorganisms in the site to reduce these contaminations, specifying necessary chemicals that we need to add if we have proper microorganism there, what kind of nutrients they need and what we need to give them to start their process. And also, it is important to know that in Canada we have 5 to 7 months of cold weather in most areas. So if the process can be done in summer, is it possible to do that in winter too, under cold conditions? Based on the well data that we had, we prepared the synthetic water to represent our groundwater. We just reduced the amount of chloride to 1000 milligram per liter to make it easier to control the stoichiometry of that. We added the same amount of chromium. We removed nitrate and nitrite because nitrate and nitrite can compete with chloride in the reaction and they disturb our result. But eventually they should be considered as some chemicals, or they can consume our electron donor too. We added the sulfate, and the pH is similar to the groundwater. It's in neutral range, 7 to 8. For nutrients and additives, we decided to use sodium acetate. We added 2200 milligram of sodium acetate based on the stoichiometry is 4 times greater than the minimum which is needed, because we didn't want to limit our experiment with the amount of electron donor. Nitrogen and phosphorus source in form of nitrogen, sorry, 500 milligram per liter, and their molar ratio is 100 to 10 to 5. Mineral solution was prepared based on ATCC 1191, and it was added to the solution 1 to 100, 1 milliliter to 100 milliliter of synthetic water. These are the series of microorganisms that we prepared. Everything was done in triplicate. So we had 3 bottles of synthetic water plus our carbon source only, which is acetate. Our synthetic water plus carbon source and minerals. The third, as you see, is synthetic water plus carbon source plus nitrogen and phosphorus without any minerals. So these two show that if adding minerals or nitrogen and phosphorus source in independently are necessary or not. At the end, we have two series similar together. They have everything: synthetic water, carbon source, nitrogen and phosphorus source, and minerals. Three for room temperature, and three bottles under cold condition in a cold chamber. For immune column, it was important to choose a proper amount that carries all the type of microorganisms from soil and groundwater to our samples without carrying chemicals. If we add lots of soil or water, we will change the concentration of our samples. So we did FDA analysis for dry soil, wet soil, and the groundwater that we took from the site. Dry soil and wet soil, they showed similar fluorescein concentration, but we didn't see anything for groundwater. We did ATP analysis for this, and based on that, it showed 222 picogram per liter of ATP. So that means our groundwater is active based on microbial activity. We decided to carry 4 gram of dry soil, 4 gram of wet soil, and 2 ml of groundwater, which is 2.5% of our each sample. That's not a lot, but it's enough to carry the enough amount of microorganism to our samples. We did the aeration method by purging by nitrogen and the aeration. So after doing it a couple of times, we could be sure that there is not any oxygen in our bottles, and microorganisms there have to use chlorate oxygen as their oxygen source. Samples were taken in an 80 days period. The chromium concentration was measured by a hack machine, and IC machine was used for concentration of chloride. As you can see in this picture, after 5 weeks, in bottles that we had acetate, nitrogen, and phosphorus sources, the appearance changed, and they are a bit cloudy and shady, while the other ones are still clear. Well, what happened here? For chromium concentration, as you can see, after 20 days, we see a sharp decline line from 3 milligram per liter to below than 1 milligram per liter, and after 50 days, it's almost 0. Actually, it's below our detection limit, so it could be considered 0. This happened only for samples they contained acetate, nitrogen, and phosphorus sources. For the samples that we had just electron donor, I mean carbon source, and carbon and minerals, we do not see any significant change on the top. You can see even after 80 days, they are in the range of 3 milligram per liter. For the sample that we had in cold condition with acetate, nitrogen and phosphorus source and minerals, the only difference that this declining trend happened in a longer time, almost maybe more than 2 times greater than that. But this shows that it's possible to reduce chromium-6 to acceptable levels even under cold condition. For chloride concentration, we have almost similar, but it happened just drastically to zero before 75 days. So we can see here it happened exactly similar to chromium reduction process for the samples with carbon source, nitrogen, and phosphorus source. For the other samples, we don't see any significant change, although they are declining, but it's not significant. For the samples that we had under cold condition in the cold chamber, they reduced the amount of chloride to zero after 80 days instead of 35 days. And again, this means it's possible to do that under cold condition. Just to make sure that our results are valid and all the amount of chloride reduced to chloride, which is non-toxic and endpoint destination of our reduction process. We measured it with IC machine, and you can see here for samples containing acetate and minerals, we do not see any significant change in the concentration of chloride, but a huge jump after 30 days for samples with acetate and nitrogen and phosphorus source, and after 58 days, it started to form in the solution in samples under cold condition. Total chlorine ions in the samples based on mole shows for the samples that we had reduction, except for the cold one, we measured more than 90% of chlorine concentration in form of chlorate or chloride. That means our mass balance is valid more than 90%. And for the sample that we had under cold condition, just we see here we have just 80% of recovery. This might be because of remaining some chlorine ion in form of chloride or hypochlorite in the solution. Now, as a result, we can say that our local microorganisms that we had in our native culture are able to reduce these contaminants, so we don't need to go for bioaugmentation and transfer some microorganism or plant from another place here to reduce the concentration of contaminants. Acetate is a proper electron donor here that could be utilized by microorganisms to reduce contaminants. Nitrogen and phosphorus are necessary elements. We have to add them in the environment if we don't have it. So microorganisms won't be able to reduce chlorate and chromate without these two. But adding minerals solution did not affect our test. And more importantly, this in situ remediation is possible under cold climate. So we don't have to change our method in winter or stop it if we want to use it all the year, and we can inject our chemicals, nutrients and substrate all the year to reduce contamination in the site. Thanks. If you have any question.
Thank you so much. Is there any questions? I don't see any questions for you at this time. The contact information is on your screen.
Yeah. If anyone has any question, just contact me and let me know.
Okay, with that ends today's webinar. Thank you everyone for attending. Thank you again to Abacus Enterprises for sponsoring today's webinar. Very much appreciate your support. Thank you to all the speakers today and our last 4 speakers, Bud, Sylvain, Matthew, and Midday. Thank you so much.
Thanks for
Reminder
having
that the presentation is next Thursday as well, the last of the series. You'll get a new link 24 hours beforehand. Reminder about EnviroTech and RemTech East coming up. Check those out. We appreciate it. And again, yes, the recordings will be available. The email link will be sent out to everyone who's registered. And on there'll be also a link to the presentations as well, the PDFs of the PowerPoints. Those should come out later today or first thing tomorrow. With that, thank you so much for attending, and we'll see you next week. Take care.